Hello there, and welcome back to Sleepwalk Space. I'm so grateful you found your way here tonight, because we're about to embark on a peaceful journey through some of the most calming and wondrous facts about our cosmos. Wherever you are right now, allow yourself to sink deeper into comfort. Let the day's worries drift away like clouds dispersing in a gentle breeze. Let your breathing slow and your mind grow quiet as we explore the universe together. Tonight, we'll discover soothing truths about the cosmos, facts that will fill you with a sense of peace and wonder. Some will surprise you, while others will settle gently into your thoughts, like soft moonlight on still water. If these peaceful explorations help you relax or spark your curiosity, consider liking and subscribing. It helps others discover this tranquil corner of the internet, one peaceful soul at a time. But for now, settle in, get comfortable, and let's begin this calming voyage through the stars. The universe is unimaginably old, having existed for nearly 14 billion years. When we look up at the night sky, we're gazing at a cosmos that has been unfolding for an almost incomprehensible span of time. Scientists estimate the universe began approximately 13.8 billion years ago. To put this in perspective, if the entire history of the universe were compressed into a single year, all of recorded human history would occupy only the last few seconds before midnight on December 31st. This vast timescale speaks to the patience of cosmic processes and the gentle, gradual way the universe has evolved from a hot, dense beginning to the cool, structured cosmos we observe today. It's a reminder that time moves differently on cosmic scales, unhurried and eternal. The Milky Way galaxy contains between 100 and 400 billion stars, each one a sun. Our home galaxy is a magnificent spiral of starlight stretching across 100,000 light-years of space. Within this vast cosmic city, somewhere between 100 billion and 400 billion stars shine, each one a blazing sphere of fusion energy like our own sun. Some are smaller and dimmer, red dwarfs that will burn for trillions of years. Others are massive blue giants that live fast and die young in spectacular supernova explosions. The sheer number of stars in our galaxy alone is staggering, yet the Milky Way is just one of hundreds of billions of galaxies in the observable universe. Each star represents a potential solar system, perhaps with planets, moons, and who knows what else orbiting in the darkness. Space is almost perfectly silent because sound needs matter to travel through. In the vacuum of space, there is no air, no medium for sound waves to propagate through. This means space is a realm of profound silence. The explosions of stars, the collisions of galaxies, the roar of rocket engines, all of these occur in complete and utter quiet. Sound requires molecules to vibrate and transmit energy, but in the near-perfect vacuum between celestial objects, such transmission is impossible. This silence is absolute and peaceful, a reminder that the cosmos operates according to different rules than our familiar earthly environment. Only electromagnetic radiation, light, radio waves, and other forms can cross the void, carrying information across the darkness without making a sound. The sun is so large that over 1 million Earths could fit inside it. Our sun, the star at the heart of our solar system, is enormous beyond easy comprehension. With a diameter of about 1.4 million kilometers, it dwarfs our planet completely. You could fit approximately 1.3 million Earths inside the sun's volume. Despite this incredible size, the sun is actually a fairly average star, neither particularly large nor particularly small compared to other stars in the galaxy. This puts our own planet into humbling perspective. We orbit a massive ball of plasma that contains 99.86% of all the mass in our solar system, held together by its own gravity, burning hydrogen into helium in its core, and providing the energy that makes life on Earth possible. Light from the sun takes about 8 minutes to reach Earth. When you feel sunlight on your skin, you're experiencing energy that left the sun's surface just over 8 minutes ago. Light travels at approximately 300,000 kilometers per second, the fastest speed possible in our universe. Yet even at this incredible velocity, it takes light 8 minutes and 20 seconds to cross the 150 million kilometers between the sun and Earth. This means when we look at the sun, we're actually seeing it as it was 8 minutes in the past. If the sun were to suddenly vanish, we wouldn't know for over 8 minutes. This delay is a gentle reminder that everything we observe in the universe is a glimpse into the past, with light serving as a messenger, carrying ancient information across the cosmic distances. Saturn's rings are made mostly of ice particles, ranging from tiny grains to house-sized chunks. The magnificent rings of Saturn are one of the solar system's most beautiful features, visible even through small telescopes from Earth. These rings are composed primarily of water ice, with some rocky material mixed in. The individual particles range dramatically in size, from microscopic ice crystals smaller than grains of sand to massive chunks of ice as large as houses or even mountains. Despite their spectacular appearance, the rings are surprisingly thin, in some places only about 10 meters thick. They orbit Saturn in a flat plane, held in place by the planet's gravity and the gravitational influences of small shepherd moons. These rings are temporary on cosmic timescales, slowly being pulled into Saturn's atmosphere, but they will remain beautiful for millions of years to come. Jupiter is so massive that it doesn't actually orbit the Sun in the traditional sense. Jupiter, the largest planet in our solar system, has a mass more than twice that of all other planets combined. It's so massive that the center of mass between Jupiter and the Sun doesn't actually lie within the Sun's surface. Instead, both Jupiter and the Sun orbit around a point in space called the barycenter, which sits just above the Sun's surface. Technically, Jupiter and the Sun orbit each other, though the Sun barely wobbles due to its much greater mass. This relationship demonstrates how gravity works as a mutual attraction, with both objects responding to each other's presence. Jupiter's immense size and gravitational influence have shaped the entire solar system, protecting inner planets from many asteroid impacts and influencing the orbits of countless smaller objects. Neptune has winds faster than the speed of sound on Earth. The distant ice giant Neptune, nearly 4.5 billion kilometers from the Sun, is a world of extreme weather. Despite receiving very little solar energy, Neptune generates powerful storms and possesses the fastest winds in the solar system. These winds can reach speeds of up to 2,100 kilometers per hour, far exceeding the speed of sound in Earth's atmosphere, which is about 1,235 kilometers per hour. Scientists aren't entirely sure what drives these incredible winds on such a cold, distant world. The energy may come from Neptune's interior heat, left over from its formation billions of years ago. These supersonic winds whip clouds of methane ice crystals around the planet, creating dynamic storm systems in Neptune's deep, blue atmosphere. There are more possible games of chess than there are atoms in the observable universe. The game of chess, despite its simple rules and limited board, contains an almost infinite depth of complexity. After just 4 moves by each player, there are over 288 billion possible positions. The total number of possible chess games is estimated to be around 10 to the power of 120, a number so large it defies imagination. By comparison, there are approximately 10 to the power of 80 atoms in the observable universe. This means there are vastly more potential chess games than there are atoms in all the stars, planets, and galaxies we can see. This staggering complexity arises from simple rules applied recursively, much like how the universe's complexity emerges from fundamental physical laws operating over cosmic time. A day on Venus is longer than a year on Venus. Venus, our neighboring planet, rotates extremely slowly on its axis. It takes Venus about 243 Earth days to complete one full rotation. However, Venus orbits the Sun in only about 225 Earth days. This creates the bizarre situation where a single day on Venus, one complete rotation, is longer than a Venusian year, one complete orbit around the Sun. Adding to the strangeness, Venus rotates backwards compared to most planets in the solar system, meaning the Sun rises in the west and sets in the east. This retrograde rotation may have been caused by a massive collision early in Venus's history, or by tidal effects from the Sun and Venus's thick atmosphere. These peculiar characteristics make Venus one of the most unusual worlds in our solar system. The footprints left by astronauts on the Moon will remain there for millions of years. When Neil Armstrong and Buzz Aldrin walked on the Moon in 1969, they left footprints in the lunar dust that will persist for an extraordinarily long time. Unlike Earth, the Moon has no atmosphere, no wind, and no water. There are no weathering processes to erode or erase these marks. The only things that will eventually disturb them are micrometeorite impacts and the very slow churning of the lunar surface caused by radiation and tiny particles from space. Scientists estimate that footprints and other artifacts left on the Moon could remain recognizable for millions of years. These permanent marks are a testament to human exploration and serve as time capsules of our first steps on another world. Neutron stars are so dense that a teaspoon of their material would weigh about 6 billion tons. Neutron stars are among the strangest and most extreme objects in the universe. They form when massive stars explode as supernovae and their cores collapse under tremendous gravitational pressure. The result is an object only about 20 kilometers in diameter, yet containing more mass than our entire Sun. The matter in a neutron star is compressed to incredible densities, with atomic nuclei crushed together so tightly that electrons and protons merge to form neutrons. If you could somehow scoop up a teaspoon of neutron star material and bring it to Earth, it would weigh approximately 6 billion tons, roughly the same as 900 Great Pyramids of Giza. This extraordinary density creates equally extreme gravity, where the escape velocity approaches half the speed of light. Black holes warp space-time so severely that time itself slows down near them. Black holes are regions of space-time where gravity is so intense that nothing, not even light, can escape once it crosses the event horizon. According to Einstein's theory of general relativity, massive objects curve the fabric of space-time, and black holes curve it to an extreme degree. This warping affects not just space, but time itself. Near a black hole, time passes more slowly compared to regions farther away. An observer falling toward a black hole would experience time normally. But to a distant observer, they would appear to slow down, taking an infinite amount of time to actually cross the event horizon. This time dilation effect, called gravitational time dilation, is one of the most mind-bending consequences of Einstein's theories, connecting the flow of time to the strength of gravity in profound ways. The coldest place in the universe that we know of is on Earth in a laboratory. While space itself is very cold, hovering around 2.7 degrees above absolute zero due to the cosmic microwave background radiation, the coldest temperatures ever achieved exist in laboratories here on Earth. Scientists have cooled atoms to within a billionth of a degree above absolute zero, temperatures far colder than anywhere naturally occurring in the cosmos. At these extreme cold temperatures, matter behaves in bizarre ways, forming exotic states like Bose-Einstein condensates, where atoms lose their individual identities and behave as a single quantum entity. These experiments help scientists understand fundamental physics and quantum mechanics. It's remarkable that the coldest known spot in the entire universe is created by human technology, right here on our planet. Mars has the largest volcano in the solar system, called Olympus Mons. Rising approximately 22 kilometers above the Martian surface, Olympus Mons is a shield volcano of staggering proportions. It's nearly 3 times the height of Mount Everest and covers an area roughly the size of Arizona. The volcano's slopes are gentle, typical of shield volcanoes formed by fluid lava flows, but its sheer scale is unprecedented in our solar system. Olympus Mons likely grew so large because Mars has lower gravity than Earth and lacks plate tectonics. On Earth, tectonic plate movement would have carried the surface away from a volcanic hotspot, creating a chain of volcanoes like the Hawaiian Islands. But on Mars, the crust remained stationary over the hotspot, allowing lava to pile up for millions of years, building this colossal mountain. The Voyager 1 spacecraft is the most distant human-made object from Earth. Launched in 1977, Voyager 1 has traveled farther from Earth than any other spacecraft. As of now, it's more than 24 billion kilometers away, well beyond the orbit of Pluto, traveling through interstellar space. Voyager 1 carries a golden record, a phonograph containing sounds and images selected to represent the diversity of life and culture on Earth, intended for any intelligent beings who might find it. The spacecraft is still operational, sending back faint radio signals that take over 22 hours to reach Earth, traveling at the speed of light. Voyager 1 is humanity's messenger to the stars, a tiny emissary carrying our greetings into the cosmic ocean, moving ever outward into the unknown. Io, one of Jupiter's moons, is the most volcanically active body in the solar system. Io is a world of fire and sulfur, constantly resurfaced by intense volcanic activity. This small moon, only slightly larger than Earth's moon, experiences extreme tidal forces from Jupiter's powerful gravity. These tidal forces flex and squeeze Io's interior, generating tremendous heat that drives its volcanism. Io has hundreds of active volcanoes, some erupting plumes of sulfur and sulfur dioxide gas hundreds of kilometers into space. The moon's surface is covered in colorful deposits of sulfur compounds, giving it a mottled yellow, orange, and red appearance. Unlike Earth's moon, which is geologically dead, Io is a dynamic, restless world where the landscape is continuously renewed by volcanic eruptions. making it one of the most geologically active places in the solar system. The Great Red Spot on Jupiter is a storm that has been raging for at least 400 years. Jupiter's most famous feature is the Great Red Spot, an enormous anticyclonic storm larger than Earth. Historical records suggest this storm has been observed for at least 400 years, though it may be even older. The Great Red Spot is a high-pressure region where winds rotate counterclockwise at speeds up to 430 kilometers per hour. The storm's distinctive red color comes from complex chemical reactions involving sunlight and the various compounds in Jupiter's atmosphere, though the exact chemistry is still not fully understood. Interestingly, the Great Red Spot has been shrinking over the past century, and scientists aren't sure why. Despite this, it remains a spectacular and enduring feature of our solar system's largest planet. Mercury has ice despite being the closest planet to the Sun. This might seem paradoxical, but Mercury, the Sun's nearest planetary neighbor, actually harbors water ice in permanently shadowed craters near its poles. While Mercury's sunlit surface reaches scorching temperatures of up to 430 degrees Celsius, the planet has almost no atmosphere to distribute heat. The floors of deep craters near the poles never see sunlight and remain perpetually frozen, with temperatures dropping to minus 180 degrees Celsius. Radar observations and data from NASA's Messenger spacecraft confirmed the presence of water ice in these cold traps. This ice may have been delivered by comet impacts over billions of years. The existence of ice on Mercury demonstrates how varied conditions can be even on a single world, with extreme heat and bitter cold existing just kilometers apart. The asteroid belt contains millions of rocky objects, but is mostly empty space. Between the orbits of Mars and Jupiter lies the asteroid belt, a region containing millions of rocky remnants from the solar system's formation. Popular culture often depicts the asteroid belt as a dense field of tumbling rocks, but the reality is far more peaceful. The asteroids are spread across such a vast volume of space that they're actually very far apart from each other. If you were to fly through the asteroid belt, you would likely see nothing but empty space in all directions. The average distance between asteroids is hundreds of thousands of kilometers. The total mass of all objects in the asteroid belt is less than that of Earth's moon. This sparse distribution means spacecraft can travel through the belt without significant risk of collision, making it a serene rather than dangerous region. Pluto's heart-shaped region is made of nitrogen ice. When NASA's New Horizons spacecraft flew past Pluto in 2015, it revealed a stunning heart-shaped feature on the dwarf planet's surface, informally named Tombaugh Regio after Pluto's discoverer. The western lobe of this heart, called Sputnik Planitia, is a vast plain of nitrogen ice, smooth and bright. This frozen nitrogen plain is thought to be relatively young, less than 100 million years old, with the ice constantly renewed through processes of sublimation and refreezing. The nitrogen ice is deep, possibly several kilometers thick, filling a large impact basin. The discovery of such dynamic geology on a small, distant world was one of the mission's greatest surprises, revealing Pluto as a complex and active body rather than a dead, frozen rock. The rings of Uranus are dark and difficult to see compared to Saturn's bright rings. While Saturn's rings are brilliant and easily visible even through small telescopes, Uranus also has a ring system, though a much more subtle one. Uranus has 13 known rings, composed of dark particles ranging from dust-sized grains to larger chunks up to 20 meters across. These particles are very dark, reflecting only a small fraction of the sunlight that hits them, making the rings extremely difficult to observe from Earth. The rings weren't discovered until 1977, when astronomers noticed stars dimming briefly as Uranus passed in front of them. The composition of the ring particles is uncertain, but they may be carbonaceous material or organic compounds darkened by radiation. These faint rings add another layer of mystery to the tilted, icy giant Uranus. Earth's moon is slowly drifting away from us at about 3.8 centimeters per year. The moon is gradually moving away from Earth due to tidal interactions between the two bodies. The moon's gravity creates tidal bulges in Earth's oceans, and the friction from these moving bulges transfers energy and angular momentum from Earth's rotation to the moon's orbit. This causes the moon to slowly spiral outward at a rate of approximately 3.8 centimeters per year. Billions of years ago, the moon was much closer to Earth, and days were shorter because Earth rotated faster. In the distant future, the moon will be farther still, and both Earth's day and the moon's orbital period will have lengthened. Eventually, the Earth-Moon system will become tidally locked, with the same face of Earth always pointing toward the moon, just as the same face of the moon always points toward Earth now. There are giant clouds of alcohol floating in space. Deep in interstellar space, astronomers have discovered enormous clouds of complex organic molecules, including ethyl alcohol, the same type of alcohol found in alcoholic beverages. One such cloud, located in a star-forming region called Sagittarius B2 near the center of our galaxy, contains enough ethyl alcohol to fill 400 trillion pints of beer. These alcohol molecules form through chemical reactions on the surfaces of dust grains in cold molecular clouds. The discovery of alcohol and other organic molecules in space is significant because it shows that the building blocks of more complex chemistry and potentially life are widespread throughout the universe. These cosmic cocktails are a reminder that space is not empty, but filled with a rich chemistry that we're only beginning to understand. The Hubble Space Telescope has taken over 1.5 million observations since its launch. Launched in 1990, the Hubble Space Telescope has revolutionized our understanding of the universe. Orbiting above Earth's distorting atmosphere, Hubble has provided incredibly sharp images of distant galaxies, nebulae, and other cosmic phenomena. Over its decades of operation, Hubble has made more than 1.5 million observations, generating about 150 terabytes of data. These observations have led to numerous discoveries, including measuring the universe's expansion rate, finding evidence for dark energy, studying the atmospheres of exoplanets, and capturing the deepest views of the universe ever seen. The Hubble Deep Field images, showing thousands of galaxies in a tiny patch of sky, transformed our perspective on the cosmos. Hubble continues to operate, working alongside newer telescopes to explore the universe. Some exoplanets orbit their stars in just a few hours. While Earth takes 365 days to orbit the Sun, astronomers have discovered exoplanets with incredibly short orbital periods. Some of these planets, called hot Jupiters or ultra-short-period planets, complete an orbit around their parent stars in just a few hours. These planets orbit extremely close to their stars, often closer than Mercury is to our Sun, experiencing intense heat and radiation. The closeness to their stars means their orbital velocities are tremendous, and they're likely tidally locked with one face permanently facing the star. These extreme worlds challenge our understanding of planetary formation and migration, as they likely formed farther out and moved inward over time. Their existence demonstrates the incredible diversity of planetary systems beyond our own. The Sun loses about 4 million tons of mass every second through nuclear fusion. At the Sun's core, temperatures reach about 15 million degrees Celsius, hot enough for nuclear fusion to occur. Hydrogen atoms fuse to form helium, releasing tremendous amounts of energy in the process. According to Einstein's equation E equals mc squared, mass and energy are interchangeable. When the Sun fuses hydrogen into helium, a tiny amount of mass is converted into energy. This amounts to about 4 million tons of the Sun's mass being converted to energy every second. Despite this enormous loss, the Sun is so massive that it has been shining steadily for about 4.6 billion years and will continue to do so for another 5 billion years before exhausting its hydrogen fuel. This fusion process is the source of all the light and heat that makes life on Earth possible. Titan, Saturn's largest moon, has lakes and seas of liquid methane and ethane. Titan is one of the most Earth-like bodies in the solar system, despite being radically different from our planet. It's the only moon with a substantial atmosphere, thicker than Earth's, composed mainly of nitrogen with a small amount of methane. Titan's surface is hidden beneath hazy orange clouds, but radar observations have revealed lakes and seas of liquid hydrocarbons, primarily methane and ethane, near the poles. These are the only stable bodies of surface liquid known to exist beyond Earth. Titan experiences a methane cycle similar to Earth's water cycle, with methane rain, rivers, and lakes. The temperature on Titan is about minus 180 degrees Celsius, cold enough for methane to exist as a liquid. This alien world provides a fascinating parallel to Earth's hydrological processes, played out in exotic materials. The Sun's core is incredibly dense, about 150 times the density of water. While the Sun appears as a glowing sphere of gas, its core is under such extreme pressure that it's far denser than any material we encounter in everyday life. The Sun's core, where nuclear fusion occurs, has a density of approximately 150 grams per cubic centimeter, or about 150 times denser than water. This incredible density is the result of the immense gravitational pressure from all the layers of the Sun pressing inward. Despite being a gas, the core is compressed to near-solid densities. The combination of extreme density and temperature creates the perfect conditions for hydrogen nuclei to overcome their electrical repulsion and fuse together, powering the Sun's radiant energy. As you move outward from the core, the Sun becomes progressively less dense, with the visible surface being much more diffuse. There are galaxies colliding right now that will eventually merge into one. Throughout the universe, galaxies are constantly interacting and merging in slow, graceful cosmic dances. These collisions take place over hundreds of millions of years, with galaxies passing through each other, their stars rarely colliding due to the vast spaces between them. However, the gravitational interactions disrupt the galaxy's structures, triggering bursts of star formation and feeding the supermassive black holes at their centers. The Milky Way itself is on a collision course with the Andromeda Galaxy, our nearest large galactic neighbor. In about 4 to 5 billion years, the two galaxies will begin to merge, eventually forming a single, larger elliptical galaxy. Astronomers have already observed many galaxy mergers at various stages throughout the universe, providing snapshots of this fundamental process in cosmic evolution. Pulsars are neutron stars that emit beams of radiation from their magnetic poles. Pulsars are rapidly rotating neutron stars that act as cosmic lighthouses, sweeping beams of electromagnetic radiation across space as they spin. These beams originate from the pulsar's magnetic poles, which are often misaligned with its rotation axis, creating the lighthouse effect. When one of these beams points toward Earth, we detect a pulse of radiation, hence the name pulsar. Some pulsars rotate hundreds of times per second, maintaining incredibly precise timing. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell, and its regular pulses were so precise that astronomers briefly wondered if they might be signals from an alien civilization. Pulsars serve as natural cosmic clocks in laboratories for testing physics under extreme conditions. Diamond rain might fall on Neptune and Uranus, deep within the ice giants. Neptune and Uranus, conditions of extreme pressure and temperature, may create an unusual form of precipitation. Scientists theorize that the methane in these planets' atmospheres is broken apart by lightning and intense pressure, forming carbon, which then crystallizes into diamonds. These diamonds would then slowly sink toward the planet's core, like rain, possibly forming a layer of liquid diamond around the core, or accumulating as solid diamond icebergs in a sea of liquid carbon. Laboratory experiments have successfully recreated the conditions thought to exist in these planets' interiors, producing nanodiamonds from hydrocarbon mixtures. While we can't yet directly observe this diamond rain, the theory is consistent with what we know about these distant worlds' compositions and internal conditions. The Sun appears white from space, but yellow from Earth due to atmospheric scattering. We often think of the Sun as yellow or orange, especially during sunrise and sunset. But this is actually an effect of Earth's atmosphere. The Sun emits light across all visible wavelengths, and when combined, this light appears white. From space, astronauts see the Sun as brilliant white. However, when sunlight passes through Earth's atmosphere, the shorter blue wavelengths are scattered more than the longer red and yellow wavelengths, a phenomenon called Rayleigh scattering. This scattering removes some of the blue light from the direct sunlight we see, making the Sun appear more yellow. During sunrise and sunset, when sunlight passes through more atmosphere, even more blue light is scattered away, leaving the red and orange hues we associate with these times of day. Ganymede, Jupiter's largest moon, is bigger than the planet Mercury. Ganymede holds the title of the largest moon in our solar system, with a diameter of 5,268 kilometers. To put this in perspective, Ganymede is larger than Mercury, which has a diameter of 4,879 kilometers, and is also larger than Pluto. Despite its size, Ganymede is a moon of Jupiter rather than a planet, because it orbits Jupiter instead of orbiting the Sun directly. Ganymede is a fascinating world with a layered internal structure, including a liquid iron core that generates its own magnetic field, the only moon known to have one. Its surface is a mix of two terrain types, heavily cratered dark regions and lighter grooved terrain with ridges and valleys. Ganymede also harbors a subsurface ocean of liquid water beneath its icy crust, making it a potentially interesting target in the search for extraterrestrial life. Astronauts aboard the International Space Station experience 16 sunrises and sunsets every day. The International Space Station orbits Earth at an altitude of about 400 kilometers, traveling at approximately 28,000 kilometers per hour. At this speed, the ISS completes a full orbit around Earth roughly every 90 minutes. This means that astronauts on board witness a sunrise or sunset every 45 minutes, experiencing 16 of each within a 24-hour period. These rapid transitions from day to night and back again create a unique experience for the crew, who must adjust their sleep schedules and daily routines accordingly. The station's windows offer spectacular views of Earth, bathed in sunlight or shrouded in darkness, with the Terminator line, the boundary between day and night, sweeping across the planet below. This perspective provides a powerful reminder of Earth's constant rotation and our planet's place in space. The temperature in the sun's corona is millions of degrees hotter than its surface. One of the great mysteries of solar physics is why the sun's corona, its outer atmosphere, is so much hotter than the surface below it. The sun's visible surface, the photosphere, has a temperature of about 5,500 degrees Celsius. Logic would suggest that moving away from the sun, temperatures should drop. However, the corona, extending millions of kilometers into space, reaches temperatures of 1 to 3 million degrees Celsius or more. This dramatic temperature increase defies our everyday experience with heat. Scientists believe the heating is caused by magnetic fields that thread through the corona, releasing energy through processes like magnetic reconnection and wave heating. Understanding this coronal heating problem is important for predicting space weather and understanding stellar atmospheres across the universe. Some meteorites found on Earth originally came from Mars. Occasionally, powerful asteroid impacts on Mars eject rocks from the Martian surface with enough force to escape the planet's gravity. These rocks wander through the solar system for millions of years, until some eventually fall to Earth as meteorites. Scientists have identified dozens of meteorites that originated on Mars, recognizing them by their unique chemical compositions and trapped gases that match the Martian atmosphere measured by spacecraft. These Martian meteorites provide rare samples of another planet that we can study directly in laboratories without the need for expensive sample return missions. They've given us insights into Mars's geology, volcanic history, and even hints about the possibility of past Martian life. One famous Martian meteorite, ALH8 4001, sparked controversy in the 1990s when some researchers claimed it contained fossil evidence of ancient Martian microbes. The solar wind is a constant stream of charged particles flowing from the sun. The sun doesn't just emit light and heat, it also continuously releases a stream of charged particles, mainly electrons and protons, known as the solar wind. This wind flows outward from the sun's corona at speeds of 300 to 800 kilometers per second, filling the solar system with a thin plasma. When the solar wind encounters Earth's magnetic field, it's mostly deflected, but some particles are funneled towards the poles where they interact with our atmosphere, creating the beautiful auroras. The boundary where the solar wind's influence ends and interstellar space begins is called the heliopause, and it marks the edge of the sun's protective bubble, the heliosphere. The Voyager spacecraft have crossed this boundary, entering the realm between stars, but they still remain gravitationally bound to the sun. Enceladus, a moon of Saturn, shoots geysers of water ice into space. Enceladus is a small, icy moon of Saturn that surprised scientists with its remarkable geological activity. Despite its frigid surface temperature of about minus 200 degrees Celsius, Enceladus has geysers near its south pole that erupt plumes of water vapor and ice particles hundreds of kilometers into space. NASA's Cassini spacecraft flew through these plumes and detected water, salts, and organic molecules, suggesting that beneath Enceladus's icy crust lies a global ocean of liquid water. The ocean is kept liquid by tidal heating from Saturn's gravity, similar to the process that drives volcanism on Io. The presence of liquid water, organic molecules, and an energy source makes Enceladus one of the most promising places in the solar system to search for extraterrestrial life. These geysers provide easy access to the subsurface ocean without the need to drill through kilometers of ice. The International Space Station is about the size of a football field. The International Space Station is the largest human-made structure in orbit and one of the most complex engineering achievements ever undertaken. When fully assembled, the ISS measures about 109 meters from one end to the other, roughly the length of an American football field, including the end zones. It has a mass of approximately 420,000 kilograms and provides about 1,000 cubic meters of pressurized living space for astronauts. The station is a collaborative project involving space agencies from the United States, Russia, Europe, Japan, and Canada. It serves as a microgravity laboratory where scientists conduct experiments in biology, physics, astronomy, and materials science. The ISS travels at 7.66 kilometers per second, orbiting Earth about 16 times per day, and has been continuously inhabited since November 2000. Light from the Andromeda galaxy takes 2.5 million years to reach us. When you look up at the night sky and spot the faint smudge of the Andromeda galaxy, you're seeing light that began its journey 2.5 million years ago. Andromeda is our nearest large galactic neighbor, located about 2.5 million light-years away. This means the light we see today shows Andromeda as it appeared in the distant past, long before modern humans evolved on Earth. Andromeda is a spiral galaxy similar to the Milky Way but slightly larger, containing about 1 trillion stars. It's one of the few galaxies approaching us rather than moving away, and it's on a collision course with the Milky Way. In about 4 billion years, the two galaxies will begin to interact and eventually merge, creating a new, larger galaxy. For now, Andromeda serves as a beautiful reminder of the vast distances and timescales at play in our universe. Water on Earth might have been delivered by comets and asteroids. One of the great questions about Earth's history is where our oceans came from. The early Earth was extremely hot, likely losing any water it initially had. Scientists believe that much of Earth's water was delivered later by impacts from comets and asteroids. Comets, often called dirty snowballs, contain significant amounts of water ice mixed with rock and organic compounds. Asteroids, particularly those from the outer asteroid belt, also contain water in the form of hydrated minerals. Over millions of years, countless impacts from these objects could have gradually built up Earth's oceans. The ratio of deuterium, heavy hydrogen, to normal hydrogen in Earth's water matches that found in certain types of asteroids more closely than comets, suggesting asteroids may have been the primary water delivery mechanism. This means the water we drink today may have traveled through space before arriving on our planet. The temperature in outer space is approximately minus 270 degrees Celsius. Space itself is almost a perfect vacuum, with very few particles to carry heat. The temperature of space is determined mainly by the cosmic microwave background radiation, the faint afterglow of the Big Bang. This radiation permeates all of space and has a temperature of about 2.7 Kelvin, or approximately minus 270 degrees Celsius. However, temperature in space is a bit misleading because there's very little matter to have temperature. An object in space will heat up or cool down based on how much radiation it absorbs from nearby stars versus how much heat it radiates away. In direct sunlight, without an atmosphere to moderate temperatures, objects can become very hot on the sun-facing side while remaining extremely cold on the shadowed side. This is why spacecraft and spacesuits require sophisticated thermal control systems. Olympus Mons on Mars is so large you couldn't see its slopes if standing on it. The sheer scale of Olympus Mons, Mars's giant volcano, creates a strange optical illusion. If you were standing on the Martian surface at the base of Olympus Mons and looking up, you wouldn't see a towering mountain rising before you. The volcano's slopes are so gradual, with an average incline of only about 5 degrees, that they would blend into the horizon. The mountain is so wide, about 600 kilometers across, that its summit would be beyond your line of sight, hidden by the curvature of Mars. Similarly, if you were standing at the summit, you wouldn't be able to see the base. The volcano's edges would extend far past the horizon in all directions. This gentle giant is so massive that it can only be properly appreciated from orbit, where its true scale becomes apparent. The core of a red giant star can be hotter than its surface was as a main sequence star. When a star like our Sun exhausts the hydrogen fuel in its core, it begins to die. But in doing so, it grows hotter at its center. The core contracts and heats up dramatically, while the outer layers expand and cool, creating a red giant. The temperature at the core of a red giant can reach over 100 million degrees Celsius as the star begins fusing helium into heavier elements. This is far hotter than the core temperature when the star was on the main sequence fusing hydrogen, which was only about 15 million degrees for a sun-like star. Meanwhile, the outer envelope of the red giant expands to enormous sizes and cools to about 3,000 to 4,000 degrees Celsius, giving it a reddish appearance. This paradox of a cooling surface and heating core represents the complex physics of stellar evolution. Europa, another moon of Jupiter, might have twice as much water as all of Earth's oceans. Europa is one of the most intriguing moons in the solar system and a prime candidate in the search for extraterrestrial life. Beneath its icy surface, Europa is believed to harbor a global ocean of liquid water. Scientists estimate this subsurface ocean could be 60 to 150 kilometers deep, containing more than twice the volume of all of Earth's oceans combined. The ocean is kept liquid by tidal heating, caused by Jupiter's immense gravity flexing Europa as it orbits. Europa's surface is remarkably smooth and young, crisscrossed by fractures and ridges, suggesting that the ice is constantly renewed. Future missions aim to study Europa more closely, possibly even drilling through the ice to sample the ocean directly. The combination of liquid water, potential chemical nutrients, and an energy source makes Europa one of the most exciting targets for astrobiology. Some stars orbit black holes so quickly they complete an orbit in just hours. At the center of our Milky Way galaxy lies a supermassive black hole called Sagittarius, a star, with a mass about 4 million times that of our Sun. Astronomers have observed stars orbiting this black hole at incredible speeds. One star, designated S2, completes an orbit every 16 years, reaching speeds of up to 7,650 kilometers per second, about 2.5% the speed of light, during its closest approach. Even more extreme are theoretical scenarios where stars could orbit black holes in just hours, whipping around at a significant fraction of light speed. These fast orbits provide opportunities to test Einstein's general relativity in extreme gravitational fields. The motion of stars around supermassive black holes offers direct evidence for their existence and allows astronomers to measure their masses with precision. The Kuiper Belt extends far beyond Pluto and contains countless icy objects. Beyond the orbit of Neptune lies a vast region of the solar system called the Kuiper Belt, a disk-shaped zone populated by thousands of icy bodies left over from the solar system's formation. The Kuiper Belt extends from about 30 AU, where Neptune orbits, to roughly 50 AU from the Sun, though some objects have even more distant orbits. Pluto is the most famous Kuiper Belt object, but it's far from alone. Other notable members include Eris, Makemake, and Haumea. These objects are primarily composed of frozen water, methane, and ammonia. The Kuiper Belt is thought to be the source of short-period comets that occasionally visit the inner solar system. Studying Kuiper Belt objects provides insights into the early solar system and the processes that formed the planets. It's a cold, dark frontier that we're only beginning to explore. Earth's atmosphere extends much farther into space than commonly thought. We typically think of the atmosphere as a thin shell surrounding Earth, but its influence extends surprisingly far. The atmosphere gradually thins with altitude, but doesn't have a sharp boundary. The Kármán line at 100 kilometers altitude is often used as the boundary between atmosphere and space, but particles of Earth's atmosphere can be detected much farther out. The exosphere, the outermost layer, extends to about 10,000 kilometers, roughly 1.6 times Earth's radius. In this region, particles are so sparse that they can travel hundreds of kilometers without colliding. Some atoms escape into space entirely, while others remain loosely bound to Earth's gravity. The geocorona, a region of hydrogen atoms surrounding Earth, extends even farther, reaching halfway to the Moon. In a sense, we and the Moon orbit within the outer reaches of Earth's extended atmosphere. The fastest spinning object in the universe is a pulsar, rotating 716 times per second. Pulsars, the rapidly rotating remnants of massive stars, can spin at mind-boggling rates. The record holder is PSR J177482446AD, a pulsar in a binary system that rotates 716 times per second. At this rotation rate, a point on the pulsar's equator is moving at about 24% the speed of light. This incredible spin is the result of conservation of angular momentum. When a massive star collapses to form a neutron star, its rotation speeds up dramatically, much like a figure skater pulling in their arms to spin faster. Some pulsars are further accelerated by accreting matter from a companion star. The fact that pulsars can spin so fast without flying apart is a testament to the incredible density and strength of neutron star material, held together by gravity so intense it overcomes the enormous centrifugal forces. Saturn is the only planet in our solar system less dense than water. Saturn is famous for its spectacular spectacular ring system, but it's also remarkable for its low density. Composed primarily of hydrogen and helium, Saturn has an average density of only 0.687 grams per cubic centimeter, which is less than water at 1 gram per cubic centimeter. This means if you could find a bathtub large enough, Saturn would float in it. Of course, this is just a thought experiment. Saturn is a gas giant without a solid surface, and its low density is an average across its entire volume. The planet's interior is under tremendous pressure and is much denser than its outer layers. Saturn's low overall density is a consequence of its composition and large size, with most of its mass distributed in a thick atmosphere of light gases. This unique property makes Saturn stand out among the planets. The term asteroid means star-like, because early astronomers couldn't resolve their shapes. When astronomers first began discovering small objects orbiting between Mars and Jupiter in the early 1800s, their telescopes weren't powerful enough to show these objects as anything other than points of light, just like stars. This is why they were called asteroids, meaning star like in Greek. Despite being much closer than actual stars, their small sizes made them appear as mere dots, even through the best telescopes of the time. It wasn't until much later, with improved technology and eventually spacecraft visits, that we learned asteroids are irregularly shaped rocky bodies rather than spheres. The name stuck, even though we now know asteroids are fundamentally different from stars. This historical naming reflects the challenges early astronomers faced in understanding the solar system with limited technology. Venus rotates so slowly that its day is longer than its year. Venus has an extremely slow rotation rate, taking about 243 Earth days to complete one rotation on its axis. Meanwhile, Venus orbits the Sun in only 225 Earth days. This creates the unusual situation where a single Venusian day, from sunrise to sunrise, is actually longer than a Venusian year. Making things even stranger, Venus rotates in the opposite direction to most planets, a retrograde rotation. If you could stand on Venus's surface and the thick clouds cleared, you would see the sun rise in the west and set in the east. The slow rotation also means Venus has no significant magnetic field, as a planet needs to rotate relatively quickly to generate a dynamo effect in its core. The reasons for Venus's slow, backward rotation aren't entirely clear, but may involve early collisions with large objects or tidal effects from the Sun. The solar system is traveling through space at about 828,000 kilometers per hour. While we think of the solar system as relatively stable, with planets orbiting the Sun, the entire solar system is itself moving through space. Our solar system orbits the center of the Milky Way galaxy at a speed of approximately 828,000 kilometers per hour, or about 230 kilometers per second. At this velocity, it takes the solar system about 230 million years to complete one orbit around the galactic center. The last time Earth was in this position in space, dinosaurs were just beginning to emerge. Additionally, the Sun is moving relative to nearby stars at about 20 kilometers per second. All of these motions combine to carry Earth on a complex path through space, orbiting the Sun while the Sun orbits the galaxy, while the galaxy itself moves through the universe. We're all cosmic travelers on multiple levels. Comets are often called dirty snowballs. Comets are icy bodies that originate from the cold outer regions of the solar system. They're composed of frozen water, carbon dioxide, methane, and ammonia, mixed with dust and rocky material, which is why they're affectionately termed dirty snowballs. Most comets reside in two regions, the Kuiper Belt beyond Neptune and the even more distant Oort cloud. When a comet's orbit brings it close to the Sun, solar radiation heats its surface, causing ices to sublimate, turning directly from solid to gas. This creates a glowing coma, a cloud of gas and dust around the nucleus, and often two tails, one of dust pushed by solar radiation, and one of ionized gas swept back by the solar wind. These tails always point away from the Sun, regardless of the comet's direction of travel. Comets are pristine remnants from the solar system's formation, and studying them provides clues about conditions in the early solar nebula. There may be a ninth planet in the outer solar system we haven't discovered yet. In recent years, astronomers have noticed peculiar orbital patterns among distant objects in the Kuiper Belt. Several trans-Neptunian objects have orbits that seem to be clustered in an unusual way that can't easily be explained by chance. Some scientists have proposed that these orbital oddities could be caused by the gravitational influence of a hypothetical ninth planet, sometimes called Planet 9 or Planet X. This proposed planet would be much farther from the Sun than Neptune, perhaps 20 times Neptune's distance, and would take 10,000 to 20,000 years to complete a single orbit. Estimates suggest it could be about 5 to 10 times Earth's mass. Despite extensive searching, no one has yet detected this planet directly, and its existence remains speculative. The search continues, and discovering a new major planet in our own solar system would be one of the most exciting astronomical findings in generations. The Moon's gravity causes Earth's oceans to bulge, creating tides. Tides are the regular rise and fall of sea levels, caused primarily by the gravitational pull of the Moon, with a smaller contribution from the Sun. The Moon's gravity pulls on Earth, and because gravity weakens with distance, it pulls slightly harder on the side of Earth closest to it and slightly less on the far side. This differential force creates two bulges in Earth's oceans, one facing the Moon and one on the opposite side. As Earth rotates beneath these bulges, locations on Earth's surface experience the cycle of high and low tides, typically 2 high tides and 2 low tides each day. The Sun also influences tides, and when the Sun and Moon align during new and full moons, their combined gravitational pull creates especially high spring tides. During quarter moons, when the Sun and Moon are at right angles, their effects partially cancel, producing smaller neap tides. Cosmic rays are not rays at all, but high-energy particles from space. Despite their name, cosmic rays are actually high-energy particles, primarily protons and atomic nuclei, that travel through space at nearly the speed of light. They were discovered in the early 1900s when scientists observed ionization in the atmosphere that increased with altitude, suggesting radiation from space. The term cosmic rays was coined before their true nature was understood. These particles originate from various sources: supernova explosions, active galactic nuclei, and possibly even more exotic events. When cosmic rays strike Earth's atmosphere, they collide with atoms, creating cascades of secondary particles called air showers. Some of these particles reach Earth's surface, passing through our bodies all the time without us noticing. Cosmic rays with the highest energies pose interesting puzzles, as their origins and the mechanisms accelerating them to such extreme speeds are still not fully understood. gold, and other heavy elements were created in the explosions of dying stars. The heavier elements in the universe, including gold, platinum, and uranium, weren't created in stars' normal fusion processes. Regular stellar fusion can create elements up to iron, but heavier elements require even more extreme conditions. These elements are forged in supernova explosions, the violent deaths of massive stars, and in the collisions of neutron stars. When a massive star explodes, the intense heat and pressure of the supernova create conditions where rapid neutron capture can occur, building up heavy atomic nuclei. Neutron star collisions produce similar conditions, creating vast quantities of heavy elements that are scattered into space. This means the gold in jewelry, the platinum in catalytic converters, and the uranium in nuclear reactors all originated in violent cosmic events billions of years ago. These elements were incorporated into the cloud of gas and dust that eventually formed our solar system, making us all products of stellar death and rebirth. The speed of light in a vacuum is the universal speed limit. One of the fundamental principles of physics is that nothing can travel faster than light in a vacuum, which moves at exactly 299,792,458 meters per second. This speed limit arises from Einstein's special theory of relativity. As an object with mass approaches the speed of light, it requires more and more energy to continue accelerating, and reaching light speed would require infinite energy. Only massless particles like photons can travel at this ultimate speed. This speed limit has profound implications for space travel and communication. Even traveling at light speed, it would take over 4 years to reach the nearest star system, over 2 million years to reach Andromeda, and an impossible amounts of time to cross the entire observable universe. The speed of light connects space and time in fundamental ways, making it central to our understanding of the cosmos. Supermassive black holes exist at the centers of most galaxies. At the heart of nearly every large galaxy, including our own Milky Way, lurks a supermassive black hole with a mass ranging from millions to billions of times that of our Sun. These cosmic monsters are thought to have formed in the early universe and grown by accreting gas and merging with other black holes as galaxies evolved. Despite their enormous mass, supermassive black holes occupy a relatively small region of space, often no larger than our solar system. The black hole at the center of the Milky Way, Sagittarius A star, has a mass of about 4 million solar masses. These black holes play a crucial role in galaxy evolution, their gravitational influence and energetic emissions when they feed affecting star formation and the distribution of gas throughout their host galaxies. Recent advances in technology have even allowed astronomers to image the shadows of supermassive black holes, confirming Einstein's predictions about these extreme objects. White dwarfs are the fates awaiting stars like our Sun. When stars like our Sun exhaust their nuclear fuel, they don't explode as supernova. Instead, they shed their outer layers as planetary nebulae and leave behind their hot, dense cores, white dwarfs. A white dwarf is about the size of Earth, but contains roughly the mass of the Sun, making it incredibly dense, about 200,000 times denser than Earth. A teaspoon of white dwarf material would weigh several tons. White dwarfs are supported against gravitational collapse not by fusion or thermal pressure, but by electron degeneracy pressure, a quantum mechanical effect. They gradually cool and fade over billions of years, eventually becoming cold, dark black dwarfs, though the universe isn't old enough yet for any black dwarfs to exist. Our Sun will become a white dwarf in about 5 billion years, after swelling into a red giant and engulfing the inner planets. Earth is the only known planet with plate tectonics. Earth's surface is divided into several large plates that float on the semi-fluid mantle below. These tectonic plates slowly move, driven by convection currents in the mantle and gravitational forces. Where plates collide, they form mountains and subduction zones. Where they pull apart, new crust forms at mid-ocean ridges. This process of plate tectonics recycles Earth's crust, shapes continents, and drives volcanic and seismic activity. Plate tectonics also plays a crucial role in regulating Earth's climate by controlling the carbon cycle through volcanic emissions and rock weathering. Interestingly, Earth appears to be the only planet in our solar system with active plate tectonics. Venus and Mars show evidence of ancient volcanic activity, but their crusts are now solid shells. Plate tectonics may be essential for maintaining a habitable planet over billions of years, making Earth unique in yet another way. The Perseid meteor shower occurs when Earth passes through debris from a comet. Every August, sky watchers are treated to the Perseid meteor shower, one of the most reliable and spectacular annual meteor showers. This celestial show occurs when Earth's orbit intersects the debris trail left behind by Comet Swift-Tuttle, a large comet that passes through the inner solar system every 133 years. As Earth plows through this stream of tiny particles, most no larger than grains of sand, they enter our atmosphere at high speeds, around 60 kilometers per second. Friction with the air heats them to thousands of degrees, causing them to vaporize in bright streaks of light, meteors or shooting stars. The Perseids appear to radiate from the constellation Perseus, hence their name. At peak activity, observers can see 50 to 100 meteors per hour under dark skies. These annual showers are a beautiful reminder of the dynamic nature of our solar system. Brown dwarfs are failed stars that never achieved fusion. Brown dwarfs occupy the fuzzy boundary between the largest planets and the smallest stars. They form like stars from collapsing clouds of gas and dust, but they don't accumulate enough mass to sustain hydrogen fusion in their cores, the process that powers true stars. Brown dwarfs typically have masses between 13 and 80 times that of Jupiter. Below 13 Jupiter masses, they can't even fuse deuterium, making them planetary mass objects. Above 80 Jupiter masses, they become red dwarf stars capable of hydrogen fusion. Brown dwarfs emit very little visible light, but glow in infrared due to the residual heat from formation, and some from deuterium fusion in the more massive ones. They slowly cool and dim over billions of years. Brown dwarfs are difficult to detect, but are thought to be relatively common in the galaxy, adding to the diversity of celestial objects. The solar maximum and minimum refer to cycles of solar activity. The Sun's activity isn't constant but varies on an approximately 11-year cycle. During solar maximum, the Sun has numerous sunspots, dark regions on its surface, caused by magnetic activity, and frequent solar flares and coronal mass ejections. During solar minimum, the Sun is quieter with few sunspots and less energetic activity. These cycles affect space weather, influencing satellite operations, communications, and even the frequency of auroras. The solar cycle is driven by the Sun's magnetic field. which flips polarity roughly every 11 years. Scientists monitor the sun's activity closely to predict space weather and protect technological systems. We're currently in solar cycle 25, which began in December 2019. Understanding these cycles helps us anticipate the sun's behavior and its effects on Earth and the solar system. Exoplanets are planets orbiting stars other than our sun. For most of human history, the only known planets were those in our solar system. That changed in the 1990s when astronomers began detecting planets orbiting other stars, called exoplanets or extrasolar planets. The first confirmed exoplanet around a sun-like star was discovered in 1995. Since then, thousands of exoplanets have been found using various detection methods, including the transit method, watching for tiny dips in a star's brightness as a planet passes in front, and the radial velocity method, detecting the wobble in a star's motion caused by an orbiting planet. These discoveries have revealed an incredible diversity of worlds: hot Jupiters, super-Earths, mini-Neptunes, and planets orbiting multiple star systems. Some exoplanets orbit within their star's habitable zone, where conditions might allow liquid water. The study of exoplanets has transformed our understanding of planetary systems and brought us closer to answering the question of whether we're alone in the universe. Io's surface is constantly renewed by volcanic eruptions. Io, one of Jupiter's 4 large Galilean moons, is the most volcanically active body in the solar system. Its surface is a patchwork of volcanic calderas, lava flows, and sulfur deposits in brilliant yellows, reds, and blacks. Io's extreme volcanism is driven by tidal heating, Jupiter's immense gravity, and the gravitational tugs from the other Galilean moons, Europa and Ganymede, squeeze and flex Io's interior, generating tremendous heat. This heat melts Io's interior rock, driving continuous volcanic eruptions. Some volcanoes erupt plumes of sulfur dioxide gas and particles that reach hundreds of kilometers into space. The volcanic activity is so intense that Io's surface is completely resurfaced approximately every million years, erasing impact craters and continually renewing the landscape. This dynamic moon offers a window into the early solar system's violent geological processes and showcases the powerful effects of gravitational interactions. The asteroid that killed the dinosaurs created a crater over 150 kilometers wide. About 66 million years ago, a massive asteroid, roughly 10 kilometers in diameter, struck Earth near what is now the Yucatan Peninsula in Mexico. The impact released energy equivalent to billions of nuclear bombs, creating the Chicxulub crater, which is approximately 150 kilometers in diameter and 20 kilometers deep. The immediate effects were catastrophic: massive tsunamis, wildfires, and shock waves. But the long-term effects were even more devastating. Dust and aerosols thrown into the atmosphere blocked sunlight, causing global temperatures to plummet in an impact winter. Photosynthesis halted, food chains collapsed, and about 75% of all species on Earth, including the non-avian dinosaurs, went extinct. This mass extinction event cleared the way for mammals to diversify and eventually for humans to evolve. The Chicxulub impact is a stark reminder of how vulnerable life on Earth is to cosmic events and the importance of monitoring potentially hazardous asteroids. Helium was first discovered in the Sun before being found on Earth. In 1868, during a solar eclipse, astronomers observed a bright yellow spectral line in the Sun's atmosphere that didn't match any known element on Earth. This mysterious line was attributed to a new element, named helium after Helios, the Greek god of the sun. It wasn't until 1895, nearly 30 years later, that helium was isolated on Earth, found in uranium ore in Norway. Helium is the second most abundant element in the universe after hydrogen, but it's relatively rare on Earth because it's so light that it escapes into space. On Earth, helium is found in natural gas deposits, where it accumulates from the radioactive decay of uranium and thorium in rocks. Helium's discovery in the Sun before Earth highlighted the power of spectroscopy, the study of light's interaction with matter, in revealing the composition of distant objects. Today, helium is used in many applications, from party balloons to cooling superconducting magnets in MRI machines. The largest known star could fill space beyond Saturn's orbit if placed at the center of our solar system. The largest stars known are red supergiants and hypergiants that dwarf our Sun. One contender for the largest is UY Scuti, a red supergiant with a radius estimated at over 1/1700 times that of the Sun. If you replace the Sun with UY Scuti, its surface would extend past the orbit of Jupiter and possibly even Saturn. These enormous stars are in the late stages of their lives, having exhausted much of their nuclear fuel and expanded dramatically. Despite their vast size, they're not the most massive stars. Their outer layers are extremely diffuse, almost vacuum-like by Earth standards. These stellar giants are relatively rare and short-lived in cosmic terms. They will eventually explode as supernovae, scattering their material into space and possibly leaving behind neutron stars or black holes. Their existence demonstrates the incredible range of stellar sizes and the dramatic transformation stars undergo as they age. Stars twinkle, but planets generally don't. When you look at the night sky, stars appear to twinkle or scintillate, their light fluctuating in brightness and color. This twinkling is not a property of the stars themselves, but an effect of Earth's turbulent atmosphere. As starlight passes through layers of air with different temperatures and densities, it's refracted or bent in slightly different directions. Since stars are so far away that they appear as point sources of light, these small refractions cause noticeable changes in brightness and position. Planets, on the other hand, are much closer and appear as small disks rather than points, even if we can't resolve the disk with our naked eyes. The light from different parts of the planet's disk averages out the atmospheric distortions, resulting in a steadier appearance. This difference is one way experienced skywatchers can distinguish planets from stars. Telescopes placed in space, like Hubble, avoid atmospheric turbulence entirely, capturing crystal-clear images without twinkling. The oldest light in the universe is the cosmic microwave background radiation. The cosmic microwave background, or CMB, is the afterglow of the Big Bang, the oldest light in the universe. It dates back to about 380,000 years after the Big Bang, when the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms. Before this recombination, the universe was opaque, filled with a hot plasma that scattered photons. Once atoms formed, photons could travel freely, and this first light has been journeying through space ever since. Over billions of years, the expansion of the universe has stretched these photons' wavelengths, shifting them from visible light to microwaves. Today, the CMB fills the entire universe with a faint, nearly uniform glow at a temperature of 2.7 Kelvin. Studying the CMB provides a snapshot of the infant universe and has been crucial in understanding the cosmology, confirming theories about the Big Bang and revealing the seeds of cosmic structure. Meteoroids, meteors, and meteorites are three stages of the same object. The terminology around space rocks can be confusing, but it follows a simple progression. A meteoroid is a small, rocky, or metallic object in space, ranging from dust-sized particles to objects several meters across. When a meteoroid enters Earth's atmosphere and burns up due to friction with air molecules, the streak of light it produces is called a meteor, commonly known as a shooting star. If a meteoroid is large enough to survive its fiery passage through the atmosphere and lands on Earth's surface, it's called a meteorite. Most meteoroids are tiny and completely vaporize, but larger ones can create spectacular fireballs and occasionally reach the ground. Studying meteorites provides direct samples of asteroids, and in rare cases Mars or the Moon, without the need for space missions. They offer invaluable insights into the solar system's formation and composition. Auroras occur on other planets too, not just Earth. The beautiful auroras seen near Earth's poles are caused by charged particles from the Sun interacting with our magnetic field and atmosphere. This phenomenon isn't unique to Earth. Other planets with magnetic fields and atmospheres also experience auroras. Jupiter has the most powerful auroras in the solar system, powered by both the solar wind and particles from volcanic Io. These Jovian auroras are much larger and more energetic than Earth's, emitting X-rays and UV light. Saturn also has auroras observed in ultraviolet light by spacecraft. Even planets without global magnetic fields can have auroras. Mars has localized crustal magnetic fields that create small-scale auroras. Uranus and Neptune, despite their tilted magnetic fields, also host auroral displays. Studying auroras on other planets helps scientists understand planetary magnetic fields, atmospheres, and the complex interactions between solar wind and planetary environments. These cosmic light shows are a reminder of the dynamic nature of our solar system. The Parker Solar Probe is the fastest human-made object. Launched in 2018, NASA's Parker Solar Probe is on a mission to study the Sun's outer atmosphere, the corona, up close. To do this, it repeatedly swings close to the Sun, using Venus gravity assists to tighten its orbit. During its closest approaches, the Parker Solar Probe reaches speeds of over 700,000 kilometers per hour relative to the Sun, making it the fastest human-made object ever. At this speed, it could travel from New York to Tokyo in less than a minute. The spacecraft also endures extreme temperatures, with its heat shield reaching about 377 degrees Celsius, while keeping its instruments at a comfortable room temperature. The Parker Solar Probe is revolutionizing our understanding of the Sun, measuring the solar wind, magnetic fields, and high-energy particles in the corona. Its observations help scientists solve long-standing mysteries, like why the corona is so much hotter than the Sun's surface. Human eyes can see the Andromeda galaxy without a telescope. On a clear, dark night far from city lights, you can see a faint, fuzzy patch in the constellation Andromeda with your naked eyes. This is the Andromeda galaxy, our nearest large galactic neighbor, located about 2.5 million light-years away. The light you're seeing left Andromeda during the Pleistocene epoch, when early humans were just beginning to use stone tools. Andromeda is the most distant object visible to the naked eye for most people, though under exceptional conditions, even more distant objects can be glimpsed. The galaxy contains about 1 trillion stars and is on a collision course with the Milky Way. In a few billion years, the two will merge. Despite being so far away, Andromeda appears about 6 times wider than the full moon in the sky, though most of it is too faint to see without optical aid. Viewing Andromeda connects us directly to the larger cosmos and the vast scales of the universe. Earth's magnetic field protects us from harmful solar radiation. Earth has a magnetic field generated by the motion of molten iron in its outer core, a process called the geodynamo. This magnetic field extends far into space, creating the magnetosphere, a protective bubble around our planet. The magnetosphere deflects most of the charged particles from the solar wind, preventing them from directly striking Earth's atmosphere and surface. Without this protection, solar radiation would gradually strip away our atmosphere, making Earth much less hospitable to life. The magnetosphere also channels some solar particles toward the poles, where they interact with the atmosphere to create auroras. Earth's magnetic field has reversed many times throughout history, with the north and south magnetic poles swapping places. The mechanisms driving these reversals aren't fully understood, but geological evidence shows they occur irregularly over thousands of years. The magnetic field is essential to maintaining Earth's habitability, shielding us from the harsh space environment. Some galaxies are moving away from us faster than the speed of light. This might sound like a violation of Einstein's relativity, which states nothing can move through space faster than light. But it's actually a consequence of the universe's expansion. Space itself is expanding, and distant galaxies are being carried along with it. For galaxies far enough away, the expansion of space between us and them can cause them to recede at speeds exceeding the speed of light. This doesn't violate relativity, because the galaxies aren't moving through space faster than light. Rather, the space between us is expanding. Light from these galaxies will never reach us because the space is expanding faster than light can travel through it. This defines the edge of the observable universe, the cosmic horizon. Only light from galaxies within this horizon has had time to reach us since the Big Bang. The expansion of space and its implications are among the most profound and counterintuitive discoveries in cosmology. There are billions of Earth-like planets in our galaxy alone. With thousands of exoplanets discovered so far, astronomers can now make statistical estimates about how common different types of planets are. Studies suggest that about 20 to 50% of Sun-like stars have planets in their habitable zones, the region where temperatures allow liquid water to exist. Given that the Milky Way contains an estimated 200 to 400 billion stars, this implies billions of potentially Earth-like planets in our galaxy alone. Of course, being in the habitable zone doesn't guarantee a planet is habitable. Many other factors matter, including atmosphere, magnetic field, geological activity, and the presence of water. Still, the sheer number of possibilities is staggering and encouraging for those searching for extraterrestrial life. As technology improves, astronomers are beginning to study exoplanet atmospheres, looking for biosignatures, chemical signs of life. The quest to find another Earth is one of the most exciting endeavors in modern astronomy. Gravitational waves are ripples in the fabric of space-time. In 2015, scientists made one of the most groundbreaking discoveries in physics by detecting gravitational waves for the first time. Predicted by Einstein's general relativity a century earlier, Gravitational waves are ripples in space-time caused by accelerating massive objects, such as merging black holes or neutron stars. When these cataclysmic events occur, they send waves spreading outward at the speed of light, stretching and compressing space itself as they pass. The LIGO and Virgo detectors can measure these incredibly tiny distortions, changes smaller than 1,000th the diameter of a proton. Detecting gravitational waves opened a new way to observe the universe, complementing traditional astronomy that relies on electromagnetic radiation. Gravitational wave astronomy has already revealed surprising populations of black holes, confirmed neutron star mergers as sources of heavy elements, and tested general relativity in extreme conditions. It's a new window into the cosmos's most violent and energetic events. The Sun will eventually become a white dwarf. In about 5 billion years, the Sun will exhaust the hydrogen fuel in its core. When this happens, the core will contract and heat up, while the outer layers expand dramatically, turning the Sun into a red giant. During this phase, the Sun will likely engulf Mercury, Venus, and possibly Earth. After burning helium in its core for about 100 million years, the Sun will shed its outer layers in a beautiful planetary nebula, leaving behind a hot, dense core called a white dwarf. This white dwarf will be about the size of Earth, but will contain about half the Sun's current mass. With no nuclear fusion to produce energy, the white dwarf will slowly cool and fade over trillions of years, eventually becoming a cold, dark black dwarf. Fortunately, this is billions of years in the future, and the Sun's transformation won't affect current life on Earth. Our star's life cycle is typical for a medium-sized star and demonstrates the natural progression of stellar evolution. Neutron stars can rotate hundreds of times per second. Neutron stars are incredibly dense remnants of massive stars that exploded as supernovae. Due to conservation of angular momentum, when a large star collapses into a tiny neutron star, it spins up dramatically, much like a figure skater spins faster when pulling in their arms. Some neutron stars, particularly those called millisecond pulsars, rotate hundreds of times per second. The fastest known pulsar rotates 716 times per second, meaning a point on its equator is moving at about 24% the speed of light. Despite these incredible rotation rates, neutron stars don't fly apart because their gravity is so intense. A neutron star's surface gravity is about 200 billion times stronger than Earth's. The study of rapidly rotating neutron stars tests the limits of physics under extreme conditions and provides insights into the behavior of matter at nuclear densities. These cosmic lighthouses are among the most extreme objects in the universe. Dark matter makes up most of the matter in the universe, but we can't see it. One of the great mysteries of modern astronomy is dark matter, a form of matter that doesn't emit, absorb, or reflect light, making it invisible to telescopes. We know dark matter exists because of its gravitational effects. Galaxies rotate faster than they should based on their visible matter alone, and galaxy clusters contain more mass than we can account for from stars and gas. Gravitational lensing, where light from distant objects is bent by massive foreground objects, also reveals more mass than we can see. Estimates suggest dark matter makes up about 85% of all matter in the universe, with ordinary matter, the stuff stars, planets, and we are made of, comprising only about 15%. Despite decades of searching, scientists haven't directly detected dark matter particles. Leading candidates include WIMPs, weakly interacting massive particles, and axions. But dark matter's true nature remains elusive, representing one of the biggest open questions in physics and cosmology. The age of the universe can be calculated from its expansion rate by measuring how fast the universe is expanding and extrapolating backward. Astronomers can estimate when the Big Bang occurred. This expansion rate is given by the Hubble constant, which relates galaxies' velocities to their distances. By combining observations of distant supernovae, the cosmic microwave background, and other data, scientists have determined the universe is approximately 13.8 billion years old. This age is consistent with other independent measurements, such as the ages of the oldest star clusters, which are about 13 billion years old. The agreement between these different methods gives confidence in our understanding of cosmic history. Measuring the universe's age precisely required overcoming many technical challenges and represents one of cosmology's great achievements. Knowing the universe's age helps us understand the timeline of cosmic evolution, from the first stars to the formation of galaxies, and ultimately to the emergence of life on Earth. Supernova explosions can outshine entire galaxies briefly. When a massive star reaches the end of its life, it can explode in a supernova, one of the most energetic events in the universe. For a few weeks, a single supernova can outshine its entire host galaxy, releasing as much energy in that brief time as the Sun will emit over its entire 10 billion year lifetime. There are different types of supernovae, but the most luminous are type Ia supernovae, which occur when a white dwarf in a binary system accumulates enough mass to trigger a thermonuclear explosion. These explosions are so bright and consistent in their peak luminosity that they serve as standard candles for measuring cosmic distances. Supernovae play a crucial role in enriching the universe with heavy elements, scattering the products of stellar nucleosynthesis into space, where they can be incorporated into new stars and planets. They're also responsible for creating neutron stars and black holes. Witnessing a supernova in our galaxy would be a spectacular, once-in-a-lifetime event. Time slows down in strong gravitational fields. One of the stranger predictions of Einstein's general relativity is gravitational time dilation, the effect where time passes more slowly in stronger gravitational fields. This has been confirmed by precise atomic clocks. A clock at sea level, in Earth's stronger gravitational field, runs slightly slower than an identical clock on a mountaintop. The effect is tiny on Earth, but near extremely massive objects like black holes, time dilation becomes dramatic. Near the event horizon of a black hole, time slows to a crawl relative to distant observers. An astronaut falling toward a black hole would experience time normally, but to someone watching from far away, the astronaut would appear to slow down, taking an infinite amount of time to cross the event horizon. This connection between gravity and time is one of the most profound insights of modern physics, revealing that time is not absolute, but depends on where you are and how fast you're moving. GPS satellites must account for time dilation to provide accurate positioning. The coldest temperature theoretically possible is absolute zero. Absolute zero, defined as 0 Kelvin or minus 273.115 degrees Celsius, is the lowest possible temperature. At this point, particles would have minimal thermal motion, existing in their lowest possible energy state. According to the third law of thermodynamics, absolute zero can never actually be reached, though scientists have cooled materials to within billionths of a degree above it. At such extreme cold, matter exhibits bizarre quantum behaviors. Gases can form Bose-Einstein condensates, where atoms lose individual identity and behave as a single quantum entity. Superfluids flow without friction, and superconductors conduct electricity without resistance. These exotic states of matter have practical applications and help physicists study quantum mechanics. Interestingly, the cosmic microwave background provides a universal temperature floor of 2.7 Kelvin throughout space, though laboratories on Earth have achieved much colder temperatures. The concept of absolute zero highlights the quantum nature of reality and the limits of what's physically possible. Our solar system orbits the Milky Way center. Just as Earth orbits the Sun, our entire solar system orbits the center of the Milky Way galaxy. The center is about 26,000 light-years away from us, and we're moving at approximately 230 kilometers per second, or about 828,000 kilometers per hour in our orbit. At this speed, it takes roughly 230 million years for the solar system to complete one orbit around the galactic center, a period sometimes called a cosmic year or galactic year. Since Earth formed about 4.5 billion years ago, our planet has made roughly 20 trips around the galaxy. The Milky Way's center harbors a supermassive black hole called Sagittarius, a star, with a mass of about 4 million suns. Our orbital motion around the galaxy, combined with the galaxy's own motion through space, means we're on a complex journey through the cosmos. All the stars we see in the night sky are fellow travelers, orbiting the galactic center along with us in this great cosmic dance. The universe's expansion is accelerating. In the late 1990s, astronomers made a shocking discovery. The universe's expansion isn't slowing down as expected, but is actually speeding up. By observing distant Type Ia supernova, which serve as standard candles for measuring cosmic distances, scientists found that these supernova were dimmer than expected, indicating they were farther away than calculations based on a steadily expanding universe predicted. This acceleration is attributed to dark energy, a mysterious form of energy that permeates all of space and exerts a repulsive pressure. Dark energy makes up about 68% of the universe's total energy content, with dark matter accounting for 27% and ordinary matter just 5%. The nature of dark energy is one of the greatest unsolved problems in physics. Its discovery earned the 2011 Nobel Prize in Physics and fundamentally changed our understanding of the universe's fate. If the acceleration continues, galaxies will eventually move so far apart that future observers won't be able to see other galaxies. Quasars are powered by supermassive black holes. Quasars are among the brightest objects in the universe, so luminous they can outshine entire galaxies. These brilliant beacons are powered by supermassive black holes at the centers of distant galaxies. As matter, gas, and dust falls toward the black hole, it forms an accretion disk that heats up to millions of degrees through friction and compression, emitting tremendous amounts of radiation across the electromagnetic spectrum. Quasars were most common when the universe was younger, between 2 and 4 billion years old, during an era of intense galaxy formation and black hole growth. Most quasars are billions of light-years away, meaning we're seeing them as they were in the early universe. The most distant quasars provide glimpses into cosmic history, less than 1 billion years after the Big Bang. Studying quasars helps astronomers understand how galaxies and supermassive black holes co-evolved, and how the early universe transitioned from darkness to the light-filled cosmos we see today. Hydrogen is the most abundant element in the universe. About 75% of the universe's ordinary matter by mass is hydrogen, the simplest and lightest element, consisting of just one proton and one electron. Helium is the second most abundant at about 24%, with all heavier elements together making up only about 1%. This composition reflects the universe's origins in the Big Bang, which primarily created hydrogen and helium. Heavier elements were formed later in stars through nuclear fusion and supernova explosions. Hydrogen's abundance makes it the primary fuel for stars, which fuse hydrogen into helium in their cores, releasing the energy that makes them shine. Hydrogen is also the main component of giant planets like Jupiter and Saturn, and it exists in various forms throughout the cosmos, in stars, giant molecular clouds, planetary atmospheres, and even thinly spread through intergalactic space. Understanding hydrogen's properties and behavior is fundamental to astrophysics and cosmology. Voyager 2 is the only spacecraft to visit Uranus and Neptune. Launched in 1977, Voyager 2 embarked on an ambitious grand tour of the outer solar system, taking advantage of a rare planetary alignment that occurs once every 175 years. After visiting Jupiter in 1979 and Saturn in 1981, Voyager 2 became the first and so far only spacecraft to fly by Uranus in 1986 and Neptune in 1989. These encounters revealed strange and unexpected features. Uranus rotates on its side with its axis tilted 98 degrees, likely due to a massive collision early in its history. Neptune surprised scientists with its active atmosphere, including the Great Dark Spot and its moon Triton, which has geysers erupting from its icy surface. Voyager 2's observations revolutionized our understanding of these ice giants. Like its twin Voyager 1, Voyager 2 continues operating and is now in interstellar space, sending back data about the boundary between the solar system and the space between stars. The Great Wall of Galaxies is one of the largest structures in the universe. The universe's large-scale structure reveals enormous filaments and walls of galaxies separated by vast voids. One of the largest known structures is the Sloan Great Wall, a vast sheet of galaxies stretching over 1.37 billion light-years across. It's part of the cosmic web, a foam-like structure where galaxies cluster along filaments of dark matter surrounding enormous voids with few galaxies. These structures formed from tiny density fluctuations in the early universe, which gravity amplified over billions of years. The cosmic web reveals how matter is distributed on the largest scales and provides insight into the universe's evolution. Despite their enormous size, these structures are still bound by gravity and are part of the observable universe's overall architecture. Mapping the cosmic web helps astronomers test cosmological models and understand the roles of dark matter and dark energy in shaping the cosmos. Light pollution affects billions of people worldwide. Light pollution is the excessive or misdirected artificial light created by human activities. It brightens the night sky, washing out stars and celestial objects, and affects billions of people who can no longer see the Milky Way from their homes. Beyond diminishing our connection to the cosmos, light pollution has real consequences. It disrupts wildlife behaviors, particularly in nocturnal animals and migratory birds, affects human health by interfering with circadian rhythms and sleep patterns, wastes energy, and contributes to climate change. Studies show that over 80% of the world's population lives under light-polluted skies, and in the United States and Europe, 99% of people experience light pollution. The good news is that light pollution is one of the most reversible forms of environmental degradation. By using better-designed lighting that directs light downward, employing motion sensors, and reducing unnecessary nighttime lighting, communities can reclaim their night skies and reduce environmental impacts. Dark sky preserves and parks are being established worldwide to protect areas where stars remain visible. Life may have started in deep ocean vents on Earth. The origin of life on Earth remains one of science's greatest mysteries, but one compelling theory suggests it began near hydrothermal vents deep on the ocean floor. These vents release hot, mineral-rich water from Earth's interior, creating environments with chemical gradients and energy sources that could have driven the first biochemical reactions. The vents provide heat, minerals, and chemical compounds that could have served as building blocks and energy sources for primitive metabolic processes. They're also protected from harmful UV radiation and asteroid impacts that would have bombarded Earth's surface billions of years ago. Modern hydrothermal vent communities teem with life, from bacteria to tube worms and other organisms that derive energy from chemicals rather than sunlight. If life arose in such environments on Earth, similar life could potentially exist around hydrothermal vents on other worlds, such as beneath the ice crusts of Europa or Enceladus, making these moons prime targets in the search for extraterrestrial life. Pluto has 5 known moons. Since Pluto's discovery in 1930, our understanding of this distant dwarf planet has grown enormously. Pluto's largest moon, Charon, was discovered in 1978. Charon is so large relative to Pluto, about half Pluto's diameter, that the two are sometimes considered a double planet system, orbiting a point in space between them. In 2005, using the Hubble Space Telescope, astronomers discovered 2 more small moons, Nix and Hydra. In 2011 and 2012, 2 additional tiny moons, Kerberos and Styx, were found. All 5 moons are thought to have formed from debris created when a large object collided with Pluto billions of years ago. The New Horizons spacecraft flew past the Pluto system in 2015, providing our first close-up views and revealing the surprising complexity and geological activity of both Pluto and its moons. These discoveries transformed Pluto from a distant, mysterious point of light into a dynamic world with a rich and fascinating history. Cosmic microwave background maps reveal the universe's baby picture. The cosmic microwave background radiation is remarkably uniform across the sky, but it contains tiny temperature fluctuations, variations of only a few millionths of a degree. These fluctuations are incredibly important because they represent density differences in the early universe, regions that were slightly denser or less dense than average. Over billions of years, gravity amplified these differences, causing matter to clump in denser regions and form galaxies, while less dense regions became voids. By precisely mapping the CMB's temperature variations, satellites like COBE, WMAP, and Planck have created baby pictures of the universe, showing what it looked like just 380,000 years after the Big Bang. These maps have allowed scientists to measure fundamental cosmological parameters, with unprecedented precision, including the universe's age, composition, and geometry. The patterns in the CMB confirm predictions of cosmic inflation and provide the seed from which all cosmic structure grew. It's a remarkable example of how studying ancient light reveals the universe's deepest secrets. The Oort cloud is a vast sphere of icy objects surrounding our solar system. Far beyond the orbit of Neptune and the Kuiper Belt lies the Oort cloud, a hypothetical spherical shell of icy debris that surrounds the entire solar system. This enormous cloud is thought to extend from about 2,000 astronomical units from the Sun. That's 2,000 times the distance from Earth to the Sun, all the way out to nearly 100,000 astronomical units, almost halfway to the nearest star. The Oort cloud is believed to contain billions or even trillions of icy objects, remnants from the solar system's formation that were flung outward by the gravitational influence of the giant planets. These objects are the source of long-period comets, those comets that take hundreds or thousands of years to orbit the Sun. Occasionally, gravitational perturbations from passing stars or the galactic tide nudge an Oort cloud object toward the inner solar system, where it becomes a spectacular comet. Despite its importance, the Oort cloud has never been directly observed because its objects are too small and distant to detect with current technology. It represents the outermost boundary of the Sun's gravitational dominion. Pulsars were initially thought to be signals from alien civilizations. When Jocelyn Bell Burnell detected the first pulsar in 1967 as a graduate student at Cambridge University, the signal was so regular and precise that it seemed artificial. The pulses came every 1.337 seconds with remarkable consistency, leading the research team to half-jokingly name it LGM-1, standing for Little Green Men 1. The possibility that this could be a signal from an extraterrestrial civilization was seriously considered. However, when more pulsating sources were discovered in different parts of the sky, each with different periods, it became clear these were natural phenomena rather than alien broadcasts. Scientists soon realized these were rapidly rotating neutron stars, the collapsed cores of massive stars, emitting beams of radiation from their magnetic poles. The discovery earned Jocelyn Bell Burnell's advisor, Anthony Hewish, the Nobel Prize in Physics in 1974. Though controversially, Bell Burnell herself was not included, despite making the initial discovery. Pulsars have since become invaluable tools in astronomy, serving as precise cosmic clocks and laboratories for testing fundamental physics. Cosmic inflation theory explains why the universe looks so uniform. In the first fraction of a second after the Big Bang, specifically between about 10 to the negative 36 and 10 to the negative 32 seconds, the universe underwent a period of exponential expansion called cosmic inflation. During this incredibly brief moment, the universe expanded by a factor of at least 10 to the 26, growing from smaller than an atom to potentially much larger than the observable universe today. This rapid expansion solved several cosmological puzzles. It explains why the universe appears so uniform in all directions. Regions that are now separated by vast distances were once close enough to reach thermal equilibrium before being stretched apart. It also explains why the universe is so flat. The rapid expansion stretched out any initial curvature like inflating a balloon. Additionally, inflation stretched tiny quantum fluctuations to cosmic scales, providing the seeds for all structure in the universe. While inflation is widely accepted, the exact mechanism that drove it remains unknown, and scientists continue to search for definitive proof through observations of the cosmic microwave background and gravitational waves from the inflationary epoch. Red shift and blue shift tell us how objects are moving. When an object emitting light moves toward or away from us, the wavelength of that light changes due to the Doppler effect, the same phenomenon that makes a siren's pitch change as an ambulance passes. If an object is moving away from us, its light waves are stretched to longer wavelengths, shifting toward the red end of the spectrum. This is called red shift. If an object is moving toward us, the light waves are compressed to shorter wavelengths, shifting toward the blue end, creating blue shift. Astronomers use this principle extensively. By measuring how much a galaxy's light is red-shifted, they can determine how fast it's moving away and estimate its distance. Nearly all distant galaxies show red shift, providing key evidence that the universe is expanding. There are a few exceptions. The Andromeda Galaxy shows blue shift because it's moving toward us and will eventually collide with the Milky Way. Red shift measurements have been crucial in discovering the universe's accelerating expansion and mapping the large-scale structure of the cosmos. The Sun contains 99.86% of all mass in the solar system. The Sun is so massive that it dominates the solar system completely, with a mass of about 2 × 10⁻³ kilograms, or about 333,000 times Earth's mass. The Sun contains approximately 99.86% of all the mass in the entire solar system. Jupiter, the largest planet, contains most of the remaining mass at about 0.1%, with all the other planets, moons, asteroids, and comets making up less than 0.04% combined. This massive disparity means the Sun's gravity governs the motions of everything in the solar system. All planets, asteroids, and comets orbit the Sun because of its overwhelming gravitational pull. The Sun's mass is also what enables nuclear fusion in its core. The pressure from all that mass squeezing the core creates the extreme temperatures needed for hydrogen atoms to fuse into helium. Without this tremendous mass, the Sun wouldn't shine, and Earth would be a frozen, lifeless rock drifting through space. The Sun's dominance is a reminder of the fundamental role gravity plays in shaping celestial systems. Stars are born in giant clouds of gas and dust called nebulae. Throughout the galaxy, there are vast regions of gas and dust called molecular clouds or nebulae, some spanning hundreds of light years across. These clouds are mostly hydrogen with a mix of helium and tiny dust grains. When a cloud is disturbed, perhaps by the shock wave from a nearby supernova or by gravitational interactions, it can begin to collapse under its own gravity. As the cloud collapses, it fragments into smaller clumps, each becoming denser and hotter. Within these collapsing clumps, protostars form, young stars in their earliest stages. The protostar continues to gather mass from the surrounding cloud, growing larger and hotter. Eventually, when the core temperature reaches about 10 million degrees Celsius, nuclear fusion ignites, and a new star is born. The remaining gas and dust around the young star may form a protoplanetary disk from which planets can eventually form. Nebulae are stellar nurseries, beautiful regions where the cycle of stellar birth continues throughout the galaxy. Famous examples include the Orion Nebula, visible to the naked eye, and the Eagle Nebula with its iconic pillars of creation. Binary star systems are more common than solitary stars. Our Sun is alone, without any stellar companion. But this is actually less common than you might think. Studies suggest that more than half of all stars exist in binary or multiple star systems, where two or more stars orbit their common center of mass. In binary systems, the stars can be very close, orbiting each other in days or hours, or widely separated, taking thousands of years to complete an orbit. These systems form when a collapsing molecular cloud fragments into multiple cores or through gravitational capture. Binary stars can interact in fascinating ways. If one star evolves into a red giant, it can transfer mass to its companion. In some cases, a white dwarf in a binary system can accrete matter from a companion star until it triggers a thermonuclear explosion, creating a Type Ia supernova. Binary systems have been crucial for measuring stellar masses, since the orbital dynamics reveal the masses of the stars involved. They also create interesting planetary environments. Planets in binary systems could have complex seasons and potentially two suns in their skies. Titan's atmosphere is thicker than Earth's. Saturn's largest moon, Titan, is the only moon in the solar system with a substantial atmosphere. In fact, Titan's atmosphere is thicker than Earth's, with a surface pressure about 1.5 times that at Earth's sea level. The atmosphere is composed primarily of nitrogen, about 95%, with methane making up most of the remainder. This thick atmosphere creates a strong greenhouse effect, but Titan is so far from the Sun that even with this warming, surface temperatures remain around minus 179 degrees Celsius. The atmosphere is so dense and hazy that the surface is completely obscured in visible light, requiring radar to penetrate the clouds and map the terrain. Titan's atmosphere undergoes a methane cycle similar to Earth's water cycle, with methane rain, rivers, and lakes. This complex atmosphere makes Titan one of the most Earth-like bodies in the solar system, despite its alien nature. The Cassini-Huygens mission revealed this strange world in detail, with the Huygens probe actually landing on Titan's surface in 2005, providing the first views from the ground of this mysterious moon. Some stars are older than the universe, or so it seemed. For years, astronomers faced an embarrassing paradox. Measurements of certain ancient stars, particularly in globular clusters, suggested they were older than the universe itself based on the universe's estimated age at the time. This seemed impossible. Stars can't be older than the universe that contains them. The problem arose from uncertainties in measuring both stellar ages and the universe's age. Determining a star's age involves understanding its composition, brightness, and evolution, all of which have uncertainties. Similarly, calculating the universe's age required precise measurements of its expansion rate, the Hubble constant, which was difficult to pin down. As measurement techniques improved and our understanding of cosmology deepened, the paradox resolved. Better measurements of the cosmic microwave background and improved stellar models brought the ages into agreement. The universe is about 13.8 billion years old, and the oldest known stars are around 13 billion years old, comfortably younger. This episode demonstrates how science corrects itself when faced with contradictions, refining measurements and theories until a consistent picture emerges. The planet Venus rotates backwards compared to most planets. Venus is peculiar in many ways, and one of its strangest features is its retrograde rotation. While most planets in the solar system rotate counterclockwise when viewed from above the Sun's north pole, Venus rotates clockwise. This means that on Venus, the sun rises in the west and sets in the east, the opposite of Earth. The reason for this backward rotation isn't entirely certain, but the leading theory is that Venus suffered one or more massive collisions with large objects early in its history, impacts powerful enough to flip its rotation. Another possibility involves tidal effects from the sun acting on Venus's thick atmosphere over billions of years, gradually slowing and eventually reversing its rotation. Venus's rotation is also extremely slow, taking 243 Earth days to complete one turn, longer than its orbital period of 225 days. Combined with its retrograde rotation, this creates a solar day on Venus, from one sunrise to the next, of about 117 Earth days. Venus challenges our understanding of planetary formation and evolution. Rogue planets drift through space without orbiting any star. Not all planets orbit stars. Throughout the galaxy, there are countless rogue planets, world-sized objects that have been ejected from their original solar systems and now wander through interstellar space alone. These planets might have formed around a star, but were flung out by gravitational interactions with other planets, or they could have formed independently from collapsing clouds of gas and dust. Without a star to provide light and heat, rogue planets are cold and dark, invisible, except through their faint infrared radiation or gravitational effects. Estimates suggest there could be billions of rogue planets in the Milky Way, possibly outnumbering stars. Some rogue planets might retain heat from their formation or from radioactive decay in their cores, potentially allowing subsurface oceans beneath icy crusts. While these worlds would be incredibly difficult to detect and study, they represent a fascinating possibility. Planets untethered from stars, floating freely through the darkness of space. The existence of rogue planets expands our definition of what a planet can be and where it can exist. The cosmic calendar compresses all of history into a single year. To help grasp the vast timescales of cosmic history, astronomer Carl Sagan popularized the cosmic calendar, which compresses the entire 13.8 billion year history of the universe into a single calendar year. On this scale, the Big Bang occurs at the first second of January 1st. The Milky Way galaxy forms around February 15th. Our solar system and Earth don't appear until September 1st, about 2/3 of the way through the year. The first life on Earth emerges around September 21st. Dinosaurs don't appear until December 25th and go extinct on December 30th. All of recorded human history, from the first civilizations to the present day, occupies only the last 14 seconds before midnight on December 31st. The entire span of a human lifetime is less than a quarter of a second. This perspective is both humbling and awe-inspiring. It shows how recent we are in cosmic history and how much time preceded our existence. The cosmic calendar helps us appreciate the deep time of the universe and our fleeting but precious moment within it. Sound waves from the early universe are frozen in the cosmic microwave background. The cosmic microwave background radiation contains more than just temperature fluctuations. It also records the imprint of sound waves that traveled through the early universe. In the first few 100,000 years after the Big Bang, the universe was filled with a hot plasma of protons, electrons, and photons. Pressure waves, essentially sound waves, rippled through this plasma, driven by the competing forces of gravity, trying to compress matter and radiation pressure, trying to push it apart. These oscillations, called baryon-acoustic oscillations, created regions of alternating high and low density. When the universe cooled enough for atoms to form and photons to travel freely, these density patterns were frozen into the distribution of matter. Today, we can detect these patterns in the cosmic microwave background as subtle variations in temperature and in the large-scale distribution of galaxies. The size of these oscillations provides a standard ruler for measuring cosmic distances and has been crucial in determining the universe's composition and geometry. These ancient sound waves are echoes from the universe's infancy, preserved for billions of years. Time dilation means astronauts age slightly slower than people on Earth. According to Einstein's theories of relativity, time passes at different rates depending on your motion and the strength of the gravitational field you're in. Astronauts on the International Space Station experience both effects. They're in a weaker gravitational field than people on Earth's surface, which causes their clocks to run slightly faster, gravitational time dilation. But they're also moving at about 7.66 kilometers per second relative to Earth's surface, which causes their clocks to run slightly slower, velocity time dilation. For the ISS, the velocity effect dominates, so astronauts age slightly slower than people on Earth. The difference is tiny. After 6 months on the ISS, an astronaut is about 0.007 seconds younger than they would have been on Earth. While this seems negligible, it's measurable and demonstrates that time is not absolute. For GPS satellites, time dilation effects are significant enough that if not corrected, position errors would accumulate at about 10 kilometers per day. These real-world applications confirm Einstein's predictions about the nature of time and space. Magnetars have the strongest magnetic fields in the universe. Magnetars are a special type of neutron star with magnetic fields so powerful they defy imagination. While typical neutron stars have magnetic fields about 1 trillion times stronger than Earth's, magnetars have fields up to 1,000 times stronger still, reaching 10 to the 15th Gauss. These magnetic fields are so intense they distort the shape of atoms, turning them into elongated cylinders. The field is strong enough that at a distance of 1,000 kilometers, it could erase the magnetic strip on every credit card on Earth. If you were unfortunate enough to be within 1,000 kilometers of a magnetar, the magnetic field would be lethal, disrupting the electrical impulses in your nervous system. Magnetars occasionally undergo starquakes, where the solid crust of the neutron star cracks and shifts, releasing enormous bursts of X-rays and gamma rays. These bursts can be detected across the galaxy. Magnetars represent some of the most extreme physical conditions in the universe, natural laboratories where physics operates at its limits. Only about 30 magnetars are known in the Milky Way, making them rare and precious subjects of study. The Fermi paradox asks where all the aliens are. Given the vast number of stars and planets in our galaxy, many of which are billions of years older than Earth, and given that life arose relatively quickly on Earth, it seems reasonable to expect that intelligent, technologically advanced civilizations should be common in the universe. Some of these civilizations would have had millions or even billions of years to develop interstellar travel and spread across the galaxy. So, where is everybody? This is the Fermi paradox, named after physicist Enrico Fermi, who famously asked this question. Many explanations have been proposed. Perhaps intelligent life is extremely rare, or perhaps civilizations tend to destroy themselves before achieving interstellar travel. Maybe space travel is harder than we think, or advanced civilizations have no interest in contacting us or spreading across the galaxy. Perhaps they're here but hiding, or we're looking in the wrong way or at the wrong time. The Great Filter hypothesis suggests there's some barrier that prevents civilizations from reaching the stage of galactic colonization. But we don't know if that filter is behind us or ahead of us. The Fermi paradox remains one of the most intriguing questions in science, touching on our place in the cosmos and the future of humanity. Jupiter's moon, Callisto, is one of the oldest surfaces in the solar system. Callisto, the second largest moon of Jupiter, has a surface that's remained largely unchanged for billions of years, making it one of the oldest landscapes in the solar system. The surface is heavily cratered, saturated with impact craters of all sizes, indicating it hasn't been resurfaced by geological activity for perhaps 4 billion years. This makes Callisto a time capsule, preserving a record of the early solar system's violent bombardment phase. Unlike Jupiter's other large moons, Io, Europa, and Ganymede, which show signs of ongoing or recent geological activity, Callisto appears geologically dead. It lacks the tidal heating that drives activity on the other moons, because it orbits farther from Jupiter and isn't in orbital resonance with the other satellites. Despite its ancient inactive surface, Callisto likely harbors a subsurface ocean beneath its ice and rock crust, detected through magnetic field measurements. This ocean makes Callisto potentially interesting for astrobiology, even though it's the least geologically active of Jupiter's large moons. Its pristine ancient surface also makes it valuable for studying the early solar system's history. Solar eclipses are a cosmic coincidence. The fact that we can experience total solar eclipses is an amazing coincidence of geometry and timing. The Sun is about 400 times larger in diameter than the Moon, but it's also about 400 times farther away from Earth. This means both objects appear almost exactly the same size in our sky, about half a degree across. When the Moon passes directly between Earth and the Sun, it can precisely cover the Sun's disk, creating a total solar eclipse. This perfect match is temporary on cosmic timescales. The Moon is gradually moving away from Earth at about 3.8 centimeters per year due to tidal interactions. Millions of years ago, the Moon was closer and appeared larger, making total eclipses longer. In the distant future, the Moon will be farther away and will appear too small to completely cover the Sun, making total solar eclipses impossible, and leaving only annular eclipses where a ring of the Sun remains visible. We live in a special era where total solar eclipses are possible. Total eclipses have been invaluable for science, allowing astronomers to study the Sun's corona and famously providing evidence for Einstein's general relativity when starlight was observed bending around the eclipsed Sun in 1919. The largest known void in space is 1.8 billion light-years across. The universe's structure includes not just concentrations of matter, but also enormous voids, vast regions with very few galaxies. The largest known void is the Boötes void, also called the Great Nothing, discovered in 1981. This supervoid is approximately 330 million light-years in diameter and contains only about 60 galaxies, far fewer than expected for a region of that size. An even larger structure, called the CMB cold spot, might represent a void 1.8 billion light-years across. This appears as a particularly cold region in the cosmic microwave background radiation, possibly indicating an enormous void along that line of sight. Voids form naturally in the cosmic web as matter is drawn toward denser regions, leaving underdense areas behind. Despite being called voids, these regions aren't completely empty. They contain some galaxies and dark matter, just at much lower densities than average. The existence of such large voids constrains cosmological models and provides information about the universe's large-scale structure. They represent the counterpoint to galaxy clusters, showing the full range of density variations in the cosmos. Betelgeuse could explode as a supernova at any time. Betelgeuse is a red supergiant star in the constellation Orion, easily visible to the naked eye as the bright reddish star marking Orion's shoulder. This massive star, with a mass about 16 to 19 times that of the Sun, is nearing the end of its life. Betelgeuse has exhausted the hydrogen in its core and is now fusing heavier elements, a process that will culminate in a catastrophic supernova explosion. In astronomical terms, Betelgeuse could explode at any time, meaning any time in the next 100,000 years. It could be tomorrow or 50,000 years from now. When it does explode, the supernova will be spectacular from Earth, possibly as bright as the full moon, and visible during the day for weeks or months. At a distance of about 640 light-years, Betelgeuse is far enough away that the supernova won't harm Earth, but close enough to provide an incredible show. The star drew attention in late 2019 and early 2020 when it dimmed significantly, leading to speculation it might be about to explode. Though it later returned to normal brightness, the dimming was likely due to dust clouds. When Betelgeuse does explode, it will be an opportunity for astronomers to study a supernova in unprecedented detail. The planets don't orbit in perfect circles. While we often depict planetary orbits as circles, they're actually ellipses, oval-shaped paths with the Sun at one focus. An ellipse's elongation is measured by its eccentricity, with 0 being a perfect circle and values approaching 1 being increasingly elongated. Most planets in our solar system have low eccentricities, meaning their orbits are nearly circular. Earth's orbit has an eccentricity of about 0.007, making it very close to circular. Mars has a more eccentric orbit at 0.093, and Mercury's is the most eccentric of the major planets at 0.206. Pluto's orbit is quite eccentric at 0.248. One reason it was reclassified as a dwarf planet, its orbit is different enough from the main planets. These elliptical orbits mean planets don't maintain constant distances from the Sun. Earth is about 5 million kilometers closer to the Sun in January than in July, though this distance variation has a much smaller effect on our seasons than the tilt of Earth's axis. Understanding orbital mechanics and elliptical orbits was one of the great achievements of early astronomy, with Johannes Kepler formulating his laws of planetary motion in the early 1600s, later explained by Newton's law of gravitation. Cosmic rays can flip bits in computer memory. High-energy cosmic rays constantly bombard Earth, and while our atmosphere absorbs most of them, some reach the surface and even penetrate underground. When a cosmic ray strikes a computer's memory chip, it can deposit enough energy to change the state of a bit, flipping a 0 to a 1 or vice versa. This is called a single event upset or bit flip. For most personal computers, this is extremely rare and usually harmless. But for critical systems like aircraft avionics, spacecraft computers, and large data centers, it's a real concern. This is why many critical systems use error-correcting memory that can detect and fix such errors. Spacecraft are particularly vulnerable since they're outside Earth's protective atmosphere and magnetic field. The computers aboard spacecraft are designed with radiation-hardened components and redundant systems to cope with this environment. Some researchers have even investigated whether cosmic rays might cause errors in biological systems, potentially contributing to mutations, though this effect is very small compared to other sources of DNA damage. The fact that particles from distant supernova can affect our technology is a reminder of our connection to cosmic events. Water bears can survive in the vacuum of space. Tardigrades, also called water bears or moss piglets, are microscopic animals less than a millimeter long, found in diverse environments worldwide. What makes them remarkable is their incredible resilience. When conditions become harsh, tardigrades can enter a state called cryptobiosis, essentially suspending their metabolism to near zero. In this state, they can survive temperature extremes from near absolute zero to over 150 degrees Celsius, pressure 6 times greater than the deepest ocean trenches, intense radiation, and even the vacuum of space. In experiments, tardigrades have been exposed to space conditions aboard satellites and returned to Earth alive, successfully rehydrating and reproducing afterward. They can survive for years in the cryptobiotic state, reviving when conditions improve. Tardigrades achieve this by replacing most of the water in their bodies with special proteins that preserve their cells. While we don't expect tardigrades to colonize space on their own, their resilience has implications for astrobiology. If life can survive space conditions, it might be transported between planets on meteorites, a process called panspermia. Tardigrades also inspire research into preserving biological materials and developing resilient organisms for space exploration. The Hubble Deep Field revealed thousands of galaxies in a seemingly empty patch of sky. In 1995, astronomers made a bold decision to point the Hubble Space Telescope at a tiny, apparently empty region of sky in the constellation Ursa Major, about the size of a pinhead held at arm's length. Over 10 consecutive days, Hubble collected light from this speck of darkness. The resulting image, the Hubble Deep Field, stunned the world. That tiny patch contained about 3,000 galaxies, each containing billions of stars. The image revealed galaxies of all types, spirals, ellipticals, and irregular galaxies, some so distant their light had traveled for over 12 billion years, showing us the universe as it was when it was very young. Later, deep field observations, including the Hubble Ultra Deep Field and the Hubble Extreme Deep Field, peered even deeper, revealing around 10,000 galaxies in similarly tiny areas. These images revolutionized our understanding of the universe's scale and evolution. They showed that galaxies fill the universe in every direction, and that the distant universe looked different from the nearby one, with more irregular and interacting galaxies. The deep field images are among the most important astronomical observations ever made, expanding our cosmic perspective and revealing the vastness of creation. Saturn's rings will disappear within 100 million years. Saturn's magnificent ring system is temporary on cosmic timescales. The rings are constantly losing material, with particles spiraling into Saturn's atmosphere in a process called ring rain. Observations suggest Saturn is losing ring material at a rate that would completely drain the rings in just 100 to 300 million years. This is a very short time cosmologically, especially considering the solar system is 4.5 billion years old. The discovery that the rings are disappearing so quickly suggests they must be relatively young, perhaps only 10 to 100 million years old. This challenged previous assumptions that the rings were as old as Saturn itself. The rings might have formed from a moon that wandered too close to Saturn and was torn apart by tidal forces, or from a moon shattered by a comet impact. Alternatively, they could be remnants from the early solar system that were temporarily captured into orbit around Saturn. The realization that the rings are young and ephemeral makes them even more precious. We're fortunate to live in an era when Saturn has rings. Future observers millions of years from now might see a ringless Saturn, making our current view a special cosmic moment. Space smells like seared steak and hot metal, according to astronauts. While you can't smell anything in the vacuum of space itself since there's no air to carry odors, astronauts have reported that when they return from spacewalks and remove their helmets, their suits and equipment have a distinctive smell. Multiple astronauts have described this smell as similar to seared meat, hot metal, welding fumes, or gunpowder. The exact source of this smell isn't entirely certain, but it's thought to come from polycyclic aromatic hydrocarbons, complex carbon molecules that form in space through various processes. These molecules cling to spacesuits and equipment during spacewalks, and then release their odor when brought back into the pressurized environment of the spacecraft. Polycyclic aromatic hydrocarbons are found throughout space, in interstellar clouds, around dying stars, and in meteorites. They're interesting to astrobiologists because they might have played a role in the origin of life. The distinctive smell of space is an unexpected sensory connection to the cosmos, a reminder that space is filled with chemistry and that human explorers experience it through all their senses. The coldest place in the observable universe is on Earth. As mentioned earlier, while the cosmic microwave background sets a temperature floor of 2.7 Kelvin throughout space, the coldest known temperatures in the universe have been achieved in laboratories here on Earth. Scientists working with ultra-cold atoms have reached temperatures as low as a few billionths of a degree above absolute zero. At these incredibly low temperatures, atoms slow to a crawl, and quantum mechanical effects become visible on macroscopic scales. Gases can form Bose-Einstein condensates, exotic states of matter where atoms behave collectively as a single quantum entity. These ultra-cold systems allow physicists to study quantum mechanics in controlled environments and have applications in developing ultra-precise atomic clocks, quantum computers, and testing fundamental physics. Creating these extreme cold temperatures requires sophisticated laser cooling and magnetic trapping techniques. The atoms are isolated in vacuum chambers and cooled by precisely tuned laser beams that slow their motion. It's remarkable that humans can create conditions colder than anywhere in the natural universe, demonstrating our ability to push the boundaries of what's possible and explore extreme physics right here on our planet. Earth's rotation is gradually slowing down. Earth's rotation isn't constant, but is gradually decreasing due to tidal friction with the moon. As the moon's gravity creates tidal bulges in Earth's oceans, The friction between these moving bulges in the ocean floor dissipates energy, slowing Earth's rotation. This effect is tiny, lengthening the day by about 1.7 milliseconds per century. But over millions of years it adds up. Geological evidence from ancient corals and tidal deposits shows that 400 million years ago, a day was only about 21.8 hours long, and a year had about 400 days. Going back further, early in Earth's history, just after the Moon formed, a day might have been only 6 hours long. As Earth's rotation slows, the Moon gradually moves farther away, currently receding at about 3.8 centimeters per year. Eventually, in the far future, Earth and the Moon will become tidally locked, with the same face of Earth always pointing toward the Moon, just as the same face of the Moon already always points toward Earth. At that point, both a day and a month would be about 47 current days long. Of course, this won't happen for billions of years, long after the Sun has evolved off the main sequence. Some galaxies are cannibals eating smaller galaxies. Galaxy mergers and interactions are common throughout the universe. Larger galaxies often grow by consuming smaller ones in a process called galactic cannibalism. The Milky Way is currently in the process of absorbing several smaller satellite galaxies. The Sagittarius dwarf elliptical galaxy is being torn apart by the Milky Way's gravity, its stars stretched into long streams that wrap around our galaxy. The Magellanic Clouds, visible from the southern hemisphere, are also being gravitationally disrupted and will eventually merge with the Milky Way. When galaxies collide and merge, the individual stars rarely collide, because the space between stars is vast. Instead, the galaxies pass through each other like ghosts, but their gravitational interactions reshape both galaxy structures. Gas clouds collide and compress, triggering bursts of star formation. Supermassive black holes at the galaxy centers spiral toward each other and eventually merge, releasing gravitational waves. The Milky Way's future collision with Andromeda is an example of a more equal merger between two large galaxies, which will create a new elliptical galaxy, sometimes called Milkomeda. These mergers are a fundamental part of how galaxies grow and evolve over cosmic time. The Moon is not perfectly spherical. While the Moon appears round, it's actually slightly egg-shaped, with its long axis pointing roughly toward Earth. This deviation from perfect sphericity is thought to have formed early in the Moon's history, when it was closer to Earth and still partially molten. Earth's gravity created strong tidal forces that stretched the Moon into this shape, which then solidified as the Moon cooled. The difference is subtle. The Moon's radius varies by only about 4 kilometers between its longest and shortest axes, but it's measurable and has consequences. This shape contributes to the Moon's tidal locking, ensuring the same face always points toward Earth. The irregularities in the Moon's shape and internal mass distribution also cause slight variations in its gravitational field, which affect orbiting spacecraft. Missions like NASA's Grail probes have mapped the Moon's gravitational field in exquisite detail, revealing mountains, craters, and mass concentrations beneath the surface. Understanding the Moon's exact shape and gravity is crucial for safely navigating spacecraft and for planning future lunar missions, including potential bases that need precise navigation and landing capabilities. Dark energy might be the cosmological constant Einstein proposed and later rejected. In the early 1900s, when Einstein developed his general theory of relativity, The prevailing belief was that the universe was static and eternal, neither expanding nor contracting. However, Einstein's equations suggested the universe should be dynamic, either collapsing under its own gravity or expanding. To make his theory compatible with a static universe, Einstein added a term called the cosmological constant, which represented a repulsive force that could counteract gravity. When Edwin Hubble discovered in the 1920s that the universe is actually expanding, Einstein reportedly called the cosmological constant his greatest blunder and removed it from his equations. But the story didn't end there. In the late 1990s, when astronomers discovered the universe's expansion is accelerating, they needed something to explain this acceleration, and the cosmological constant made a comeback. Today, the cosmological constant is one leading candidate for explaining dark energy, the mysterious force driving the accelerated expansion. If dark energy is the cosmological constant, it represents a fundamental property of space itself, an intrinsic energy density that doesn't dilute as space expands. Einstein's supposed blunder might actually have been profound insight ahead of its time. The nature of dark energy remains one of physics' biggest mysteries. Some stars have planets made of diamond. As astronomers discover more exoplanets, they're finding worlds with compositions unlike anything in our solar system. Some planets orbiting pulsars or white dwarfs might be made largely of carbon in the form of diamond or graphite. These carbon planets could form in environments with a high carbon-to-oxygen ratio, unlike our solar system, which has more oxygen. One example is 55 Cancri E, a super-Earth orbiting very close to its star. Models suggest that if this planet has enough carbon and the right conditions, a significant portion of its mass could be diamond. The planet is about twice Earth's size and 8 times its mass, and at least a third of it might be diamond, though it would be subject to intense heat and pressure, making it very different from gemstone diamonds. Another candidate is PSR J11719, 1438b, a planet orbiting a millisecond pulsar that might be the compressed remnant of a star, possibly consisting largely of crystalline carbon. While these diamond worlds might sound glamorous, they would be hostile environments, nothing like the precious gems we value. Still, they demonstrate the incredible diversity of planets in the universe. The tallest mountain in the solar system is on an asteroid, while Olympus Mons on Mars is often cited as the tallest mountain in the solar system. The asteroid Vesta has a central peak in its Rhea Silvia crater that rivals or possibly exceeds Olympus Mons in height. This peak rises about 22 kilometers above the crater floor, though measuring heights on irregularly shaped asteroids is more complex than on planets. Vesta is the second largest object in the asteroid belt, about 525 kilometers in diameter. The Rhea Silvia crater is enormous, about 500 kilometers across, nearly the size of Vesta itself, suggesting it was created by a massive impact that almost shattered the asteroid. The central peak formed as material rebounded after the impact. NASA's Dawn spacecraft studied Vesta in detail from 2011 to 2012, revealing its surprisingly complex geology. Vesta has a differentiated interior with a crust, mantle, and core, much like the rocky planets, making it more like a small planet than a typical asteroid. Studying Vesta provides insights into planet formation and the early solar system, and its towering peak demonstrates that impressive geological features can exist on even small bodies. Mercury has ice in craters, but is also one of the hottest places in the solar system. Mercury experiences some of the most extreme temperature variations in the solar system. On the side facing the Sun, surface temperatures can reach 130 degrees Celsius, hot enough to melt lead. But because Mercury has almost no atmosphere to distribute heat, and because it rotates very slowly, nighttime temperatures plunge to minus 180 degrees Celsius. Despite the extreme heat on sun-facing surfaces, permanently shadowed craters near Mercury's poles remain eternally frozen. These craters are so deep that sunlight never reaches their floors, creating cold traps where temperatures stay below minus 170 degrees Celsius year-round. Water ice and possibly other frozen volatiles accumulate in these craters, delivered by comet impacts over billions of years. The existence of ice on the solar system's innermost planet seems paradoxical, but demonstrates how local conditions can create surprising environments. Understanding Mercury's ice deposits has implications for resource utilization in future space exploration and provides clues about volatile delivery throughout the inner solar system. Mercury's extreme temperature swings and hidden ice make it one of the solar system's most fascinating worlds. There are more trees on Earth than stars in the Milky Way. A 2015 study estimated there are approximately 3 trillion trees on Earth, about 400 trees for every person alive. This vastly exceeded previous estimates and came from combining satellite imagery with ground measurements from around the world. For comparison, astronomers estimate the Milky Way contains between 100 billion and 400 billion stars, meaning Earth has roughly 8 to 30 times more trees than our galaxy has stars. This comparison helps put both numbers in perspective. The Milky Way, spanning 100,000 light-years and containing countless worlds, has fewer stars than the number of trees on our single planet. It's a reminder of how abundant life can be and how unique Earth is as far as we know. Unfortunately, the study also found that humans cut down about 15 billion trees per year, and the total number of trees has fallen by about 46% since the start of human civilization. Protecting Earth's forests is crucial, not just for biodiversity and climate, but also for maintaining this remarkable abundance of life. When we look at the stars, we can remember that our planet hosts a richness that rivals the galaxy itself. Neutron stars have mountains, but they're only millimeters tall. The surface of a neutron star is extraordinarily smooth because gravity is so intense that it crushes any irregularities. The tallest mountains on a neutron star would be only about a millimeter high, though this represents an enormous amount of matter due to the star's incredible density. Despite their tiny size, these mountains have significant effects. As the neutron star rotates, any asymmetry in its shape or mass distribution generates gravitational waves. These are incredibly weak, but next-generation gravitational wave detectors might be able to detect them. The neutron star's crust, where these mountains exist, is thought to be incredibly strong, possibly the strongest material in the universe. It consists of a lattice of atomic nuclei squeezed together at densities comparable to atomic nuclei themselves, with electrons flowing between them. Deeper inside, matter becomes even more exotic, possibly forming a quark-gluon plasma or other states of matter that can't be replicated in laboratories. Studying neutron stars pushes our understanding of physics to its limits. exploring matter under conditions that can't be found anywhere else in the universe. The solar system is moving through space at 514,000 miles per hour. Not only does the solar system orbit the Milky Way's center, but the entire galaxy is also in motion. The Milky Way is moving toward the Andromeda galaxy at about 110 kilometers per second as part of their eventual collision. Both galaxies are also moving as part of the Local Group, a collection of more than 50 galaxies, including the Milky Way, Andromeda, and numerous smaller galaxies. The Local Group itself is being pulled toward the Virgo supercluster, a massive collection of galaxy clusters about 65 million light-years away. Additionally, there's an even larger mass concentration in the direction of the constellations Centaurus and Hydra, sometimes called the Great Attractor, which influences the motion of our Local Group and thousands of other galaxies. When you add up all these motions, Earth is moving through the cosmic microwave background rest frame at about 370 kilometers per second, or roughly 514,000 miles per hour. We're cosmic travelers on an epic journey through the universe, our motion shaped by the gravitational pull of structures on the largest scales. This motion is so smooth and constant that we don't feel it, but it connects us to the grand cosmic dance. You can see the International Space Station with the naked eye. The International Space Station is one of the brightest objects in the night sky and is easily visible to the naked eye under the right conditions. When the ISS passes overhead during twilight, when the ground is in darkness, but the station is still illuminated by the sun, it appears as a bright point of light, moving steadily across the sky. It can be as bright as Venus and take several minutes to cross the sky from horizon to horizon. The ISS orbits Earth every 90 minutes at an altitude of about 400 kilometers, so it makes multiple passes over any given location each day, although not all passes are visible. NASA and other space agencies provide websites and apps that predict when the ISS will be visible from your location. Watching the ISS pass overhead is a powerful reminder that humans are living and working in space right above us. Inside that moving point of light are astronauts from different countries conducting experiments, maintaining the station, and looking down at Earth. It's a beautiful connection between those of us on the ground and those exploring space above, a reminder of human achievement visible in the night sky. The universe's oldest known object is a star called Methuselah, HD 1.283, nicknamed the Methuselah star, is one of the oldest known stars in the universe. Located about 190 light-years from Earth in the constellation Libra, this subgiant star has been the subject of intense study because its estimated age initially appeared to exceed the age of the universe itself. Early measurements suggested the star was about 16 billion years old, older than the universe's estimated age of 13.8 billion years, creating an obvious paradox. However, more precise measurements using the Hubble Space Telescope refined the star's age to 14.5 billion years, plus or minus 0.8 billion years. With this uncertainty, the star's age is consistent with the universe's age, resolving the paradox. Methuselah is a metal-poor star, meaning it contains very few elements heavier than hydrogen and helium, indicating it formed when the universe was very young, before many generations of stars had enriched the cosmos with heavier elements. Studying ancient stars like Methuselah provides insights into the early universe and the first generations of stars. These ancient stellar relics are windows into cosmic history, survivors from an era when the universe was fundamentally different from today. Some moons have moons called moon moons or submoons. The question of whether moons can have their own moons has intrigued astronomers and spacecraft mission planners. Theoretically, if a moon is large enough and orbits far enough from its planet, it could have a stable orbit around itself, where a smaller moon or submoon could exist. However, the gravitational influence of the parent planet creates tidal forces that make such orbits unstable in most cases. The smaller moon would likely be ejected from orbit or crash into its parent moon over time. Despite this, some researchers have identified regions around certain moons where moons might be stable, at least temporarily. Large moons like Ganymede, Callisto, Titan, and Earth's moon have regions where small satellites could potentially orbit. As far as we know, no natural moons have been discovered in our solar system, but artificial ones exist. Spacecraft that orbit moons are technically moons. The Lunar Reconnaissance Orbiter circles Earth's moon, making it a moon. The concept illustrates the complex gravitational dynamics in multi-body systems and reminds us that stable orbits depend on the delicate balance of competing gravitational forces. Space is not a perfect vacuum. While space is often described as a vacuum, it's not completely empty. Interstellar space contains about 1 atom per cubic centimeter on average, mostly hydrogen. This is extraordinarily low density. Earth's atmosphere at sea level contains about 10 to the 19th molecules per cubic centimeter, but it's not zero. In denser regions like molecular clouds where stars form, the density can reach thousands or even millions of atoms per cubic centimeter. Still a far better vacuum than anything we can create in laboratories, but dense by space standards. Intergalactic space is even more rarefied, with perhaps 1 atom per cubic meter. Space also contains cosmic rays, photons from stars in the cosmic microwave background, neutrinos, dark matter, and various fields including gravitational and magnetic fields. Even empty space itself has energy. The quantum vacuum fluctuates with virtual particles constantly popping into and out of existence, a phenomenon confirmed by the Casimir effect. This vacuum energy might be connected to dark energy. Far from being an empty void, space is a dynamic environment filled with matter, energy, and fields, though at densities almost incomprehensibly lower than our everyday experience. Voyager 1's golden record contains sounds and images from Earth. Both Voyager spacecraft carry identical golden records, 12-inch gold-plated copper phonograph records, containing sounds and images selected to represent the diversity of life and culture on Earth. The records were curated by a committee chaired by Carl Sagan and include 116 images showing scientific information, human anatomy, landscapes, and scenes from daily life. The audio portion contains greetings in 55 languages, sounds from nature including wind, thunder, animal calls, and surf, and musical selections from around the world ranging from Bach to Chuck Berry to traditional music from many cultures. The records also include printed messages from President Jimmy Carter and UN Secretary-General Kurt Waldheim, along with diagrams showing Earth's location using pulsars as reference points. The records are encased in protective aluminum jackets, with instructions for playing them etched on the surface. The chances of the records ever being found by an extraterrestrial civilization are extraordinarily small, but they serve as time capsules of humanity, messages in bottles cast into the cosmic ocean. They represent our hope and optimism, our desire to reach out and say we were here, we existed, and this is what we created and valued. The sun's energy takes thousands of years to travel from its core to its surface. While light travels from the sun's surface to Earth in just over 8 minutes, the energy that eventually escapes as sunlight has a much longer journey. Nuclear fusion in the sun's core produces high-energy gamma-ray photons. These photons can't travel directly out of the sun because the sun's interior is incredibly dense, filled with plasma that constantly absorbs and re-emits photons. Each photon travels only a tiny distance before being absorbed by an atom and then re-emitted in a random direction. This process, called the random walk, means photons zigzag their way outward, taking an extraordinarily long path. Calculations suggest it takes between 10,000 to 170,000 years for energy to random walk from the core to the surface, with most estimates around 100,000 years. During this journey, the photons are gradually downgraded in energy through countless absorption and emission events, converting from high-energy gamma rays to lower-energy visible light and infrared radiation by the time they reach the surface. This means the sunlight we see today comes from fusion reactions that happened during the last ice age or even earlier. It's a humbling thought that connects us to the deep past. Earth's atmosphere extends farther than the moon. While we typically think of Earth's atmosphere as ending at the Kármán line, 100 kilometers up, the outermost layer, called the geocorona, extends much farther. The geocorona is a tenuous cloud of hydrogen atoms that reaches at least 630,000 kilometers from Earth, or about 1.6 times the Earth-Moon distance. This was discovered by analyzing data from the SOHO spacecraft. The geocorona is incredibly diffuse, containing only a few dozen atoms per cubic centimeter even at its densest, making it essentially undetectable except with specialized instruments. These hydrogen atoms come from water vapor in Earth's lower atmosphere that's broken apart by ultraviolet radiation and then escape upward. While the moon orbits within this extended atmosphere, the density is so low it has no practical effect. The geocorona does affect astronomical observations by emitting a faint glow in ultraviolet wavelengths. Understanding Earth's extended atmosphere is important for interpreting astronomical data and for understanding how atmospheres interact with space environments. It's a reminder that the boundaries between Earth and space are gradual and complex, rather than sharp dividing lines. Billions of years from now, the sun will become a red giant and destroy Earth. The sun is currently about 4.6 billion years old and is roughly halfway through its main sequence lifetime. In about 5 billion years, it will exhaust the hydrogen fuel in its core. When this happens, the core will contract and heat up, while the outer layers will expand enormously, swelling into a red giant. The sun's surface will extend past the orbit of Mercury and Venus, and possibly reach Earth's current orbit. Earth might be engulfed and destroyed, or it might barely escape as the sun loses mass and Earth's orbit expands outward. Even if Earth isn't directly consumed, it will be rendered utterly uninhabitable. The oceans will boil away, the atmosphere will be stripped off, and the surface will be roasted to temperatures of hundreds or thousands of degrees. After spending about 1 billion years as a red giant, fusing helium in its core, the sun will shed its outer layers in a beautiful, interplanetary nebula and leave behind a white dwarf about the size of Earth, slowly cooling for trillions of years. This is the fate awaiting our solar system, though it's so far in the future that life on Earth will likely have either gone extinct or evolved beyond recognition. Or perhaps humanity will have spread to other star systems long before the sun's death. And as we reach the end of our journey through these calming cosmic facts, let yourself drift deeper into rest. The universe continues its ancient rhythms while you sleep. Stars slowly turning in their galactic dance, planets orbiting in silent precision, light traveling across unimaginable distances. You are part of this grand cosmos, made of the same elements forged in ancient stars, connected to everything through the invisible threads of gravity and light. Let these thoughts settle gently around you like stardust, peaceful and eternal. May you sleep soundly, wrapped in the quiet majesty of the universe. Thank you for joining me on this peaceful exploration. Sweet dreams and good night.